Long after the last voices disappeared, the structures remained. They watched forests advance, rivers shift, kingdoms rise, and generations pass until the worlds around them became almost unrecognizable. Yet ancient walls still cross forgotten landscapes. Stone entrances still open into darkness. Massive foundations remain buried beneath later civilizations, while isolated monuments stand beneath the same stars their builders once observed. They are the last witnesses to places we can never see as they truly were. Archaeology can recover fragments of their stories, but some details have survived without their explanations. And within those missing pieces lie questions that thousands of years have failed to erase. Today, we journey to these ancient survivors and explore the mysteries they still refuse to surrender.
Teutoburg Forest in North Rhine-Westphalia, Germany, holds a line of sandstone towers rising beside the town of Hornbad Meinberg. This is Externstein, not a temple built block by block, but a natural cliff system turned into chambers, stairways, platforms, bridges, altars, and carvings. Its mystery is not whether the stones are real. The mystery is how much of this vertical landscape was engineered by human hands, and how far back that engineering truly goes. Externstein was never discovered in the modern sense. Medieval documents mention the area by the 12th century, and the rocks were later used as a Christian hermitage and chapel. Archaeological work in the 20th century found traces of prehistoric human presence, including stone tools linked to late Ice Age hunters. But most carved structures visible today are usually dated to the Middle Ages. That is where the problem begins. The site looks older than its written history, but the hard evidence does not easily support every legend attached to it. Geologically, Externstein is already extraordinary before a single tool mark is considered. The rocks are made of Osning sandstone, formed roughly 100 million years ago in the early Cretaceous, when this region lay near a shallow sea. Later tectonic pressure tilted the layers almost upright, and erosion stripped away softer material, leaving narrow pillars that rise up to about 37 to 40 meters. 13 main rocks are usually numbered by researchers, but the most dramatic features concentrate around the first 5. Unlike megalithic sites such as Stonehenge, where humans transported and raised separate stones, Externstein began as a vertical geological accident. The builders did not add mass, they removed it. The main grotto in Rock 1 contains several chambers connected by passages. Measurements recorded by site descriptions show rooms only a few meters across, with ceiling heights around 2.5 meters. These are not natural caves in the ordinary sense. They are spaces adjusted for human movement, worship, storage, or ritual use. One chamber carries evidence of an altar consecration in the early 12th century. Another domed chamber feels almost artificial in its geometry, as if the carvers were trying to impose architecture on stone that never wanted to become a building. The first technical puzzle is access. Many of the worked areas are not at ground level. Platforms, stairs, openings, and chambers sit above steep drops. To carve them, workers needed stable footing, repeated access, and a way to remove debris. A modern visitor climbs with rails, steps, and bridges. The original workers may have used timber scaffolding, wooden ladders, rope systems, or temporary platforms pinned into the stone. Yet few direct traces of this construction infrastructure survive. The finished monument remains, but the temporary machine that made it has vanished. Externstein becomes especially strange when one studies its stairways. Rock 3 is even known as the Stair Rock, and the carved routes between the rocks include narrow steps, steep ascents, small landings, and passages that force the body into controlled movement. These stairways are not grand ceremonial ramps like those at Teotihuacan. nor broad processional stairs like those of Maya temples. They are tight, almost surgical cuts in the stone, often only wide enough for a single person. Their function was not crowd movement, they controlled access. This is where the engineering mystery sharpens. A stair carved into living rock cannot be adjusted like a wooden stair. If one step is too high, too shallow, or too narrow, the mistake remains. If the angle is wrong, the entire climb becomes dangerous. The carver must plan the route before cutting deeply, because every strike removes material that cannot be put back. In masonry architecture, a bad block can be replaced. In rock-cut architecture, the cliff itself is the blueprint, the material, and the final structure at the same time. The narrowness of the Externstein stairs suggests a builder thinking in 3 dimensions. The steps had to connect different natural surfaces without weakening the pillar. They had to follow cracks and avoid unstable zones. They had to be steep enough to gain height quickly, but not so steep that a person could not climb with tools, lamps, offerings, or ritual objects. They also had to survive rain, frost, and thousands of footfalls. In a region where water can enter sandstone pores, freeze, expand, and break the surface, every carved edge is vulnerable. The survival of these stairs shows that their makers understood, at least through experience, which parts of the stone could be cut and which parts had to be left untouched. The most puzzling part is not that medieval workers could carve stone. They certainly could. Europe in the 12th century produced cathedrals, towers, reliefs, vaults, and complex stone sculpture. The question is why so much effort was invested into making a natural rock formation behave like a sacred building. The high chamber, the platforms, the carved openings, the possible altar zone, and the stairways together create a vertical route. A visitor does not simply enter Externstein. He ascends it. The body moves from ground level to chamber, from chamber to stair, from stair to platform, from platform to sky. That movement is architectural, even if the architecture was carved from a cliff. Another debated feature is the circular opening in the high chamber. Some researchers have argued that it may align with sunrise around the summer solstice. This idea is famous but controversial. The alignment is not enough by itself to prove a prehistoric observatory. Many medieval chapels used light symbolically, and later damage or rebuilding may have changed the original geometry. Still, the possibility matters because it shows how precisely the upper space was shaped. Whether the opening was astronomical, liturgical, or symbolic, it was not randomly placed. It directs light into a controlled interior. The large descent from the cross relief adds another layer. It is about 5 meters high and 4 meters wide, and art historians commonly date it to around 1160 to 1170. If that dating is correct, it is one of the oldest monumental rock reliefs north of the Alps. This makes Externstein not only a geological landmark but a medieval sculptural experiment. The relief proves that artisans here were capable of cutting large religious imagery directly into natural stone. The same tradition of tool control may help explain the chambers and stairways, yet it does not explain every stage of the site's development. The deeper mystery is chronology. Excavations found evidence of late Ice Age activity in the wider rock shelter area, including microlithic tools from hunter-gatherer groups. But between that prehistoric presence and the medieval chapel, the archaeological record is thin. Legends connect Externstein with pagan Saxon worship and the Irminsul, the sacred pillar said to have been destroyed under Charlemagne. But archaeology has not confirmed a continuous cult site from the Bronze Age or Iron Age. That absence is important. A responsible documentary cannot claim Externstein was certainly a prehistoric temple. It can only say that the rocks attracted humans very early, and that later builders transformed them with unusual precision. Along the rugged Mediterranean coast of southwestern Turkey, where mountains plunge directly into the sea. The ruins of forgotten cities lie scattered among pine forests and limestone cliffs. At first glance, Baie de Glary Coastal National Park appears to be a landscape of natural beauty, but hidden within it are ancient harbours, stone cities, tombs carved into mountainsides, and engineering achievements that continue to challenge modern understanding. Although many ruins were known locally for centuries, systematic archaeological investigations intensified during the 19th and 20th centuries, and researchers soon realized that this coastline had once been one of the most strategically important regions of the ancient Lycian world. What they discovered was not merely a collection of ruins, but evidence of sophisticated engineering systems whose full technological foundations remain uncertain today. One of the first puzzles confronting archaeologists is geographical rather than architectural, as the ancient inhabitants of Lycia developed thriving urban centres in an environment that seems fundamentally hostile to large-scale construction. The Baie de Glary mountain range rises sharply from the Mediterranean, creating steep slopes, unstable terrain, and limited agricultural land. Yet cities such as Phaselis and Olympus flourished here for centuries. Modern urban planners would immediately identify serious challenges, since transporting construction materials through mountainous terrain dramatically increases labour costs. Establishing reliable water supplies requires extensive hydraulic infrastructure, and building ports along rocky coastlines demands detailed understanding of marine conditions. Yet ancient builders not only overcame these obstacles but transformed them into advantages, as their settlements occupied positions that maximized trade opportunities while maintaining access to natural defensive features. The question is not whether they succeeded, because the ruins prove that they did, but rather how they accumulated enough practical knowledge to consistently make such effective engineering decisions without modern surveying instruments, geological studies, or hydrodynamic models. Among all the engineering enigmas of Baie de Glary Coastal National Park, none is more fascinating than the harbour system of Phaselis, which, unlike most ancient ports, possessed 3 separate harbours positioned around a narrow peninsula extending into the Mediterranean Sea. Even today, marine engineers regard harbour construction as one of the most complex forms of infrastructure, as successful ports must account for wave energy, prevailing winds, seasonal storms, sediment transport, water depth, coastal erosion, and long-term environmental change. Modern projects rely on satellite measurements, sonar mapping, computer simulations, meteorological records, and extensive geological surveys. Yet the builders of Phaselis had none of these technologies. Despite this, archaeological surveys indicate that the city's harbours functioned effectively for centuries, serving merchant vessels moving between the Aegean, Anatolia, Cyprus, Egypt, and the Levant. The engineering challenge becomes clearer when comparing Phaselis with other famous ancient ports, as the Roman harbour of Ostia near Rome required constant maintenance because of sediment accumulation from the Tiber River. The harbour of Alexandria underwent repeated modifications as coastal conditions changed, and even many modern marinas struggle with silting problems that reduce navigability over time. Phaselis, however, appears to have been positioned with remarkable awareness of local marine dynamics, and researchers still debate how ancient engineers identified the most stable locations, whether through generations of sailors accumulating detailed observational knowledge of seasonal currents, builders conducting long-term monitoring of wave behavior before construction, or the existence of a sophisticated body of maritime engineering knowledge that has since disappeared. No surviving texts provide definitive answers, and the deeper researchers investigate the harbour system, the more impressive it becomes, as the harbours were not simply natural coves but were integrated into a broader urban network involving roads, warehouses, defensive structures, and commercial facilities. suggesting planning on a scale requiring significant expertise in logistics and transportation engineering, while the knowledge behind that planning remains largely invisible. Closely connected to the harbour mystery is the question of surveying, as modern surveyors can establish accurate coordinates using GPS systems capable of centimetre-level precision, whereas ancient Lycian builders relied on simple instruments, visual alignments, and practical experience. Yet many structures throughout the region display remarkable spatial organisation, with roads connecting strategically important locations, harbour entrances aligning with navigational requirements, and urban layouts demonstrating awareness of topography and drainage patterns. This raises an intriguing possibility that ancient surveyors possessed practical methods whose effectiveness modern observers tend to underestimate, since archaeologists know that Greek and Roman engineers used measuring rods, plumb lines, grommers, and sighting instruments. But what remains unclear is how these relatively simple tools consistently produced results that functioned effectively within highly complex environments. The gap between available tools and achieved outcomes continues to fuel debate among historians of technology. The Mediterranean climate presents another engineering challenge, as rainfall is highly seasonal. Summers are long and dry, and extended drought periods can place severe pressure on urban populations. Yet the ancient settlements within Beda Glari maintained reliable water supplies over long periods. Excavations have revealed reservoirs, cisterns, aqueduct components, drainage channels, and storage facilities, and together these systems indicate advanced understanding of hydraulic management. The mystery lies in the calculations, since modern engineers use mathematical models to estimate consumption rates, storage capacity requirements, evaporation losses, and seasonal variability, while ancient engineers lacked such computational tools. Nevertheless, they repeatedly constructed systems capable of supporting substantial populations, and although researchers can reconstruct the physical infrastructure and estimate volumes and capacities, they cannot fully reconstruct the decision-making process behind the designs. Questions remain about how builders determined the optimal size of reservoirs, how accurately they could predict annual water demand, and how they accounted for population fluctuations, drought cycles, or changing environmental conditions, with the answers remaining uncertain. Southern Turkey lies within an active tectonic region, and over the last 2,000 years numerous earthquakes have affected the eastern Mediterranean, causing many ancient cities to be damaged or destroyed, yet portions of Lycian and Roman structures within Beda Glari remain standing. This persistence presents another engineering puzzle, as traditional explanations often emphasize luck or favorable geology. But some researchers argue that ancient builders may have understood practical principles of seismic resistance. Massive stone blocks were frequently arranged in ways that distributed loads effectively. Foundations often rested directly upon stable bedrock, and structural designs incorporated flexibility through layered construction techniques. Comparable questions arise at sites such as Machu Picchu in Peru, where earthquake-resistant stonework continues to astonish engineers, and at Hattusa in Anatolia, where massive fortifications survived centuries of environmental stress. The evidence suggests that ancient builders possessed a far more sophisticated understanding of structural behavior than is sometimes assumed, although whether this knowledge resulted from formal engineering traditions or generations of accumulated experience remains unknown. The Lycian rock-cut tombs scattered throughout the region introduce another unresolved technological question, as many were carved directly into steep cliff faces, and even today, creating such monuments would require extensive planning, specialized access systems, and significant safety precautions. Ancient craftsmen somehow managed to cut symmetrical facades, maintain geometric proportions, and execute detailed decorative work in locations that appear extraordinarily difficult to reach, making the challenge not simply artistic but also logistical and engineering related. Workers needed stable platforms, methods for transporting tools and materials, and surveying techniques capable of maintaining accuracy while working on vertical surfaces. And although archaeologists can study the finished monuments, they still struggle to reconstruct the precise construction processes. What do you think was the true secret behind the lost engineering knowledge of the Lycian builders? Centuries of accumulated experience, a forgotten scientific tradition, or technologies that history has simply failed to preserve? Share your thoughts in the comments below. Civilizations do not normally build more than 100 temples without a clear, unified design. Yet in the rugged landscape of Aihol, along the banks of the Malaprabha River, a contradiction emerges that challenges both logic and historical expectation. Dating primarily between the 6th and 8th centuries CE under the Chalukya dynasty, this site contains over 120 structures, each one slightly different, each one seemingly testing a new idea. The mystery is not just what Aihol is, but what it was trying to become. Unlike other ancient centers where architectural evolution follows a gradual and traceable progression, Aihol compresses experimentation into a single geographic space. Styles that should be separated by centuries appear side by side. Forms that belong to different cultural traditions coexist without clear hierarchy. The result feels less like a finished city and more like a controlled environment, an ancient laboratory of stone. Aihol was not discovered in the traditional sense. Local communities had always known of its existence, but systematic study began during the 19th century under the Archaeological Survey of India. Early documentation revealed something unusual. These temples were not built in a linear sequence, but in overlapping phases, often modifying or reinterpreting earlier designs. One of the most important clues comes from the Maguti Jain temple inscription, dated to approximately 634 CE. This inscription anchors Aihol historically, linking it to the Chalukya king Pulakeshin II. However, archaeological analysis shows that many structures predate and postdate this inscription, suggesting continuous experimentation over multiple generations. Excavations have uncovered not only foundations and structural modifications, but also evidence of architectural adjustments mid-construction, walls shifted, columns repositioned, and layouts altered. Such changes imply that builders were not simply executing plans, they were revising them in real time. The most unsettling mystery at Aihol lies not in its diversity, but in its precision. Many of the temples were constructed using dry stone techniques, blocks fitted together without mortar. Yet the joints are so exact that even modern measuring tools struggle to detect gaps beyond fractions of a millimeter. From an engineering perspective, this level of accuracy exceeds functional necessity. A stable structure does not require such perfection. In fact, in many ancient systems, slight irregularities help distribute stress more evenly. Yet at Aihol, stones are cut and aligned with a degree of geometric control that suggests an advanced understanding of load transfer and material behavior. Consider the placement of stone beams and ceiling slabs. Some of these elements weigh several tons, yet they are supported by relatively narrow columns. Modern structural analysis indicates that the load distribution in such systems depends on precise alignment of contact surfaces. A deviation of even a few degrees could significantly increase stress concentrations. The builders of Aihol appear to have anticipated this, achieving tolerances comparable to finely machined components. When compared to Roman engineering such as the arches of the Colosseum, the contrast becomes clear. Roman builders relied on arches and concrete to redistribute forces efficiently across curved surfaces. At Eye-hole, however, the approach is fundamentally different. Instead of dispersing stress through curvature, the structures concentrate load through carefully controlled Nakort Teepsukdar, stone contact points, almost as if the builders were experimenting with micro-load balancing systems. There is also evidence of interlocking mechanisms in certain structures, where stones are shaped to fit into each other in ways that prevent lateral movement. This technique, while known in other ancient cultures, appears here in a more experimental and inconsistent form, as if multiple solutions were being tested simultaneously. The question that emerges is unavoidable. Why invest such effort into precision that provides no immediate practical advantage? One possibility is that Eye-hole served as a testing ground for structural optimization, an attempt to understand how stone behaves under different conditions. Another, more controversial hypothesis suggests that the builders possessed a theoretical framework, perhaps a form of early applied geometry or proto-engineering science, that has not survived in written form. Eye-hole is often described as the cradle of Indian temple architecture, but this label does not fully capture its complexity. The site contains early examples of multiple architectural traditions: the northern Nagara style, the southern Dravida style, and the hybrid Visara form. What is unusual is not their presence but their coexistence. In most historical contexts, these styles emerge in different regions and evolve over time. At Eye-hole, they appear together, sometimes within a single structure. The Durga temple, for instance, features an apsidal plan reminiscent of earlier Buddhist Chaitya halls, combined with elements that would later define Hindu temple architecture. Meanwhile, the Ladkhan temple resembles a secular assembly hall with a flat roof supported by massive stone beams, lacking the vertical emphasis typical of later temples. Such diversity suggests that Eye-hole was not bound by a single religious or cultural framework. Instead, it appears to have been a place where ideas were tested, combined, and reinterpreted. Many ancient structures align with celestial events, but Eye-hole presents a more complex pattern. While some temples are oriented toward the east, others deviate slightly, creating variations in how sunlight enters the interior spaces. These deviations are not random. Observations suggest that different temples produce distinct light patterns at different times of the year. In certain cases, sunlight illuminates specific parts of the structure only during particular seasons, hinting at a deliberate manipulation of solar angles. Compared to monuments like Stonehenge, which exhibit precise alignment with solstices, Eye-hole's approach appears less about exact calibration and more about exploring a range of possibilities. This raises the possibility that the site functioned as a form of experimental observatory, where builders studied the interaction between architecture and light. Perhaps the most intriguing aspect of Eye-hole is its apparent incompleteness. Many structures show signs of partial construction, finely carved bases supporting unfinished upper sections, or detailed columns beneath rough, unpolished stone surfaces. In most archaeological contexts, such features indicate interruption, war, resource shortages, or abandonment. But at Eye-hole, the pattern repeats across multiple sites, suggesting something else entirely. If these were prototypes rather than final products, their incomplete state may have been intentional. Each structure could represent a stage in an ongoing process, a snapshot of experimentation rather than a failed project. So what do you think Eye-hole really was, an ancient architectural laboratory? Or something even more advanced that we still don't understand? Drop your thoughts in the comments below. Deep within the Orăști Mountains of modern-day Romania, a fortress built more than 2,000 years ago continues to challenge archaeologists, engineers, and military historians. Perched high above steep valleys and protected by dense forests, Costesti Setuiei was once one of the strongest strongholds of the Dacian kingdom. Yet the greatest mystery is not why it was built, but how its builders achieved such remarkable engineering with technology that should have been far more limited than what the ruins suggest. Although known locally for centuries, systematic archaeological investigations began during the 19th and 20th centuries as researchers explored the network of Dacian fortresses surrounding Sarmizegetusa Regia, the ancient capital of Dacia, and excavations gradually revealed walls, towers, terraces, defensive systems, roads, workshops, and evidence of sophisticated construction techniques hidden beneath centuries of vegetation and soil, showing that what emerged was not a primitive hill fort but a carefully engineered military complex. The first mystery begins with location, as Costesti Setuiei occupies a steep mountain ridge, roughly 600 meters above sea level, where even today transporting construction materials into the area is difficult. Yet the Dacians managed to construct massive defensive walls, towers, platforms, and supporting infrastructure using thousands of tons of stone and timber. The challenge becomes apparent when comparing the site to other famous ancient mountain complexes such as Machu Picchu in Peru, where Inca builders transported stone across mountainous terrain with no wheeled transport, or Sacsayhuaman, where enormous blocks weighing dozens of tons were moved uphill, making Costesti Setuiei a similar logistical puzzle under very different environmental conditions. Archaeologists estimate that many stones used in the fortress originated from quarries located kilometers away, meaning every block had to be extracted, shaped, transported, positioned, and integrated into defensive structures without modern machinery. And while no written Dacian engineering manuals survive and no detailed construction records exist, the physical evidence remains even though the knowledge system behind it has largely disappeared, raising the simple question of how a society often portrayed by Roman sources as tribal could coordinate construction projects of such complexity across rugged mountain landscapes. The most fascinating mystery of Costesti Setuiei is a construction technique known today as muros de secus, which at first glance appears relatively ordinary, but upon closer examination reveals something far more sophisticated, consisting of two parallel faces of carefully cut stone blocks with the interior filled with earth, gravel, and smaller rocks, while massive wooden beams tie the entire structure together by penetrating the stone faces and connecting the wall into a unified system. To modern engineers, this arrangement looks surprisingly familiar because rather than relying solely on the compressive strength of stone, the design distributes stress through multiple materials working together, with stone handling compression, wood absorbing tension and dynamic movement, and the internal fill dissipating energy and stabilizing the structure, resembling in modern terminology a composite engineering system. The mystery lies in the fact that such principles are generally associated with much later structural design philosophies, and researchers studying reconstructed sections have noted that muros de secus behaves differently from conventional dry stone walls, appearing capable of absorbing shock, accommodating minor ground movement, and resisting collapse more effectively than many simpler fortification designs, with some engineers even suggesting that the combination of stone and timber may have offered advantages during seismic activity, although the exact degree of earthquake resistance remains debated. What deepens the mystery is the absence of a clear developmental pathway, as Greek fortifications use different approaches, Roman military walls followed different principles, and Celtic fortifications sometimes incorporated timber-lay structures. But muros de secus possesses distinctive characteristics not easily explained as a direct copy of neighbouring traditions, leading to questions about whether the Dacians independently discovered these structural concepts, whether knowledge travelled through networks now lost to history, or whether archaeologists are seeing only the final product of centuries of experimentation that left little trace in the archaeological record, with no consensus existing even more than 2,000 years after construction, as the walls continue to raise questions that modern engineering cannot answer with certainty. The fortress reveals another surprising feature in its precision, as laser surveys and archaeological mapping have shown that the defensive structures were not placed randomly according to the terrain, but instead followed carefully planned layouts where terraces align with defensive objectives, walls maximize natural advantages, observation points maintain strategic visibility over approaches, and movement corridors channel attackers into predictable routes, all of which required accurate surveying. This is where the mystery becomes significant because the Dacians possessed no total stations, laser levels, GPS receivers, drones, or digital mapping systems. Yet they successfully transformed an irregular mountain landscape into an integrated defensive machine, similar to how ancient builders elsewhere achieved comparable feats, such as Roman engineers surveying roads across continents, Egyptian architects aligning pyramids with extraordinary precision, and the Inca designing cities perfectly adapted to mountainous terrain. Placing Costesti's Setatui within this category of engineering achievements, where the ruins demonstrate the result while the process remains largely invisible. Costesti's Setatui was never intended to operate alone, but formed part of a larger defensive network that included multiple fortresses protecting the Dacian heartland. And while each fortress appears impressive when viewed individually, collectively they reveal something much more remarkable as communication routes linked strategic positions, observation points, monitored valleys and mountain passes, fortified sites controlled movement through the region, and resources and manpower could be coordinated across significant distances. Military historians often compare the system to a distributed defensive network rather than a collection of isolated strongholds, raising the important question of how advanced Dacian organizational capability was, since building a single fortress requires planning, but constructing an interconnected mountain defense system requires administration, logistics, engineering, communication, and long-term strategic thinking, which helps explain the fierce Dacian resistance described in Roman sources during Emperor Trajan's campaigns in the early 2nd century AD, as the fortresses were not simply walls, but components of a regional military architecture. Every mountain fortress faces the same challenge of water, as a garrison cannot survive without reliable access to fresh water, especially during a siege. And at Costesti Setatui, archaeologists have uncovered evidence suggesting sophisticated management of water resources through terraces, drainage systems, and strategic placement of structures that indicate builders carefully considered hydrology. Although this may sound routine, it was not, because mountain environments are notoriously difficult for long-term settlement, where too little water creates vulnerability and too much water destabilizes slopes, damages foundations, and accelerates erosion. Yet the fortress survived for centuries because its builders successfully balanced these competing forces, achieving results comparable to modern geotechnical engineers who routinely analyze drainage before constructing on steep terrain, even though the Dacians did so without modern hydrological science, leaving unclear how they accumulated this knowledge. Costesti Setatui has withstood over 2,000 years of harsh conditions, freezing winters, heavy rains, erosion, and seismic activity, yet much of the fortress remains intact. Foundations still stand, defensive layouts are visible, and terraces shape the landscape. This durability suggests the builders had a strong understanding of stable terrain and long-lasting construction methods, even though their knowledge has been lost. In the harsh, semi-arid highlands of the Aures Mountains in modern-day Algeria, far from major rivers and deep within a landscape defined by heat, dust, and scarcity, lies the remains of Lambaesis, once the headquarters of the powerful Legio III of Augusta under the authority of the Roman Empire. At first glance, it appears to be just another Roman military camp, but the deeper archaeologists look, the more one question dominates the site. How did a highly complex, permanently occupied military city, complete with water systems, hospitals, administrative centers, and training academies function for decades in an environment that should not have been able to sustain it at all? Unlike legendary sites lost to myth, Lambaesis was never entirely forgotten, its ruins remaining visible and scattered across the Algerian plateau until systematic study began in the 19th century during French colonial expeditions. Early surveys revealed inscriptions carved into stone blocks, official Latin texts referencing military drills, discipline, and speeches delivered to soldiers, and these unusually detailed records, far more structured than those found at many other Roman sites, immediately suggested that Lambaesis was more than a simple frontier outpost. By the late 19th and early 20th centuries, archaeologists uncovered a carefully organized layout, including a central principia aligned with near-geometric precision, extensive barracks capable of housing thousands of soldiers, a valetudinarium indicating long-term medical infrastructure, and large open courtyards likely used for training and assembly, all pointing toward a permanent and highly disciplined occupation. Later excavations throughout the 20th century expanded this picture even further, revealing road networks extending outward from the camp and connecting it to nearby settlements such as Timgad, suggesting that Lambaesis functioned not in isolation but as part of a broader regional system. Yet with each new layer uncovered, the same contradiction became increasingly difficult to ignore. The infrastructure was too advanced, too permanent, and too dependent on resources for the harsh environment in which it existed. The greatest unresolved mystery of Lambaesis lies beneath its stones in water, because the site preserves evidence of a sophisticated hydraulic system that includes aqueducts channeling water from distant sources potentially spanning tens of kilometers, large underground cisterns coated with waterproof materials such as opus signinum, and an internal distribution network that delivered water across the camp with remarkable efficiency. In a region where annual rainfall is low and evaporation rates are extremely high, sustaining a population of several thousand soldiers would have required an immense and continuous water supply. And when placed into measurable context, the scale becomes even more striking. A Roman legion of approximately 5,000 men, the standard size of units like the Legio III Augusta, would require at least 20 to 30 litres of water per person per day for drinking, cooking, and sanitation, resulting in a daily demand exceeding 100,000 litres, not including water for animals, industrial processes, or inevitable losses through evaporation and leakage. Yet despite this enormous demand, there is no major perennial river located nearby, making the existence of such a system deeply puzzling. Comparisons with other Roman sites only intensify the mystery, because at Vindolanda in Britain, water supply relied on abundant rainfall and nearby streams, while at Carnuntum, proximity to the Danube ensured stable and predictable access. But Lambaesis operated in a marginal environment where such reliability should not have been possible. Several hypotheses attempt to explain this contradiction, including the idea that Roman engineers possessed a far more detailed understanding of regional hydrology than currently documented, allowing them to exploit hidden or seasonal water sources, while others suggest that underground aquifers, perhaps now depleted, once provided more abundant reserves than we see today, and a more controversial theory proposes that the hydraulic system may have been partially inherited or constructed upon earlier undocumented infrastructure. However, even if water could be sourced, maintaining such a system across long distances would require continuous technical oversight to prevent leakage, manage sediment buildup, and ensure consistent flow, meaning that Lambesis was not merely using water, but actively controlling it in a way that appears disproportionate to both its environmental constraints and the technological assumptions we typically assign to the period. The architectural and epigraphic evidence suggests that Lambesis functioned as far more than a conventional military base, because inscriptions found on site describe formal speeches delivered by commanding officers that outline discipline, tactical expectations, and organizational hierarchy in a manner resembling institutional doctrine rather than routine operational orders, indicating a level of administrative complexity rarely preserved in other frontier camps. The presence of large assembly halls and carefully structured training spaces further supports the idea that Lambesis operated as both a training academy and an administrative center, not simply as a place where troops were stationed. While its geographic position near the frontier zones between Roman-controlled territory and desert regions, inhabited by indigenous groups, places it at a strategic but isolated node within the empire's defensive network. This combination of features raises a compelling possibility that Lambesis may have served as a central command hub coordinating military operations across North Africa, functioning in a role similar to a regional headquarters where strategy, logistics, and communication were organized on a large scale. If this interpretation is correct, then the scale and complexity of the site begin to make sense. Yet it introduces an even deeper question. Why would such a critical command center be established in a location defined by extreme logistical challenges rather than in a more resource-rich and accessible environment? Among the most intriguing discoveries at Lambesis are its inscriptions, which differ significantly from typical Roman dedicatory or commemorative texts because many of them are highly procedural, detailing military routines, disciplinary systems, and even elements of rhetorical instruction intended for officers and soldiers alike, suggesting a standardized approach to communication and training. However, certain irregularities within these inscriptions have drawn the attention of researchers, including repeated phrasing patterns that deviate from classical Latin syntax, unusual abbreviations that are not widely attested in other regions of the empire, and structural formatting that appears systematic yet remains only partially understood. While some historians interpret these anomalies as local linguistic adaptations or shorthand used within a specific military context, others propose a more speculative interpretation in which these inscriptions may represent early forms of coded or semi-coded communication systems designed to standardize complex information across different units, allowing for more efficient transmission of doctrine and orders. Although there is no definitive evidence that these texts constitute true encryption, the possibility suggests that Lambesis may have been a site where Roman military organization reached an advanced level of abstraction and systemization that is rarely visible in the archaeological record, hinting at a layer of operational sophistication that remains difficult to fully reconstruct. By the 3rd century CE, Lambesis began to decline, yet unlike many ancient sites, its transformation does not appear to have been triggered by a single catastrophic event, as there is no clear evidence of widespread destruction, no extensive burn layers, and no definitive signs of sudden abandonment caused by invasion or natural disaster. Instead, the site seems to have undergone a gradual reduction in importance, eventually losing its central role as the Legio III Augusta was disbanded and later reorganized during periods of instability within the Roman Empire, suggesting a slow administrative shift rather than a violent collapse. Even so, this explanation does not fully resolve the mystery. because if Lambasis depended heavily on its complex water system, any disruption, whether technical, environmental, or political, could have had cascading effects on its ability to function. Yet no single cause has been definitively identified, leaving the site's decline as ambiguous as its rise. When each component of Lambasis is examined individually, it can be explained within the known capabilities of Roman engineering and military organization, including advanced construction techniques, efficient logistical planning, and strategic territorial control. Yet when all these elements are considered together, the site presents a paradox in which a large, permanent, and resource-intensive military complex not only existed, but operated successfully within an environment that should have imposed severe limitations on its sustainability. Compared to other Roman sites, Lambasis does not necessarily exceed the technical limits of the empire, but it applies those capabilities in a context where they seem least viable, making it stand out as a case where known technology was pushed into conditions that challenge our assumptions about its practical application. Do you think Lambasis was simply the result of Roman engineering at its peak, or could it be evidence of knowledge we still don't fully understand? Share your thoughts in the comments below. Overlooking the Guadalbolon Valley near Jaén in southern Spain stands an ancient Iberian city that may preserve one of the most precise solar alignments ever discovered in pre-Roman Europe. At Puente Tablas, a gate built more than 2,500 years ago, appears to have been designed to capture the sunrise of the winter solstice with astonishing accuracy, and the structure still works today, raising the question of how its builders achieved it. Although the hill had long been known locally, systematic archaeological excavations began during the late 20th century, revealing not a simple settlement but a fortified Iberian oppidum, covering roughly 6 hectares and occupied primarily between the 7th and 4th centuries BCE. Excavations uncovered houses, defensive walls, ritual spaces, towers, and eventually a discovery that transformed the site into one of the most important archaeological mysteries in Spain, as the eastern gate of the city appeared to be aligned with a specific astronomical event. At first, this seemed unlikely because ancient gates are often oriented according to terrain, defense, or convenience, yet repeated observations suggested something far more deliberate. Every year around the winter solstice, the shortest day of the year, the rising sun appears on the southeastern horizon at its most southerly point, and at Puente Tablas, archaeologists observe that sunlight entering through the eastern gate follows a carefully controlled path and illuminates a sacred area beyond the entrance, a phenomenon that occurs only during a narrow seasonal window and carries extraordinary implications. To understand why, consider the challenge facing ancient engineers, as the position of sunrise changes every day throughout the year, and at the latitude of Jaén, approximately 38 degrees north, the sunrise point shifts across a large section of the horizon between summer and winter, meaning that identifying the precise position of the winter solstice requires years of observation. Unlike modern astronomers, the Iberians possessed no telescopes, precision optics, GPS systems, digital clocks, or computerized models, yet the gate alignment appears intentional. Researchers studying the site have suggested that the builders may have tracked solar movements for generations before construction began, requiring a sophisticated tradition of astronomical knowledge passed from one generation to another. The mystery becomes deeper when compared with other ancient solar monuments, such as the famous Passage Tomb of Newgrange in Ireland, which captures sunrise during the winter solstice, Stonehenge, which aligns with important solar events, and the temples of ancient Egypt, which often incorporated astronomical orientations. Yet Puente Tablas belongs to a civilization that left far fewer written records, and although the monument demonstrates a level of astronomical precision comparable to some of the most famous ceremonial sites in the ancient world, the knowledge system behind it remains largely invisible. Questions remain unanswered, including how Iberian builders determined the correct angle, how many years of observations were required, whether they used fixed markers on surrounding hills, and whether specialized astronomer priests were responsible for the measurements, as no definitive answers have emerged. At first glance, the Eastern Gate appears defensive, but closer examination reveals a more complex design in which the entrance forces movement through controlled pathways, preventing approaching visitors from walking straight into the city and instead manipulating visibility, movement, and perspective. This combination of military and ceremonial functions presents another puzzle, as modern architects often separate sacred and defensive spaces, yet at Puente Tablas they seem deliberately integrated. The builders created an entrance capable of controlling armies while simultaneously functioning as a giant astronomical instrument, demonstrating remarkably sophisticated dual-purpose engineering. And even more surprising is that no surviving Iberian text explains how the design process worked, leaving the structure intact but the methodology unknown. Building an astronomical alignment requires much more than observing the sun, as it also requires surveying, and while today surveyors rely on laser instruments, satellite positioning systems, total stations and digital elevation models capable of measuring terrain with centimetre-level precision, the engineers of Puente Tablas possessed none of these technologies. Nevertheless, the city occupies a strategically selected hilltop overlooking the surrounding valley, with defensive walls following terrain contours efficiently, access routes carefully controlled, and visibility across the landscape maximized. This raises an important question about how ancient surveyors measured angles, elevations, distances, and sightlines accurately enough to combine military requirements with astronomical precision. Experimental archaeologists have attempted to reproduce ancient surveying methods using ropes, wooden stakes, plumb lines, and observation poles, and while such techniques can achieve impressive results, reproducing the exact accuracy seen at Puente Tablas remains challenging, suggesting that the final structure reflects knowledge far beyond simple trial and error. Excavations reveal that the city was protected by substantial fortifications, with walls, towers, gates, and restricted access points working together as a coordinated defensive system. Military historians often compare effective ancient fortifications to mechanical devices in which every component serves a specific function, and removing one element weakens the entire defensive strategy. And Puente Tablas appears to follow this principle as the gate channels movement, the walls exploit natural terrain, and the towers extend observation range, allowing the entire system to operate as an integrated design. What remains unclear is how such knowledge developed, as many ancient societies improved defenses gradually over centuries through warfare and adaptation. Yet parts of Puente Tablas appear surprisingly mature from an engineering perspective, giving the impression that builders already understood sophisticated defensive concepts before construction began, leaving the origin of that expertise unanswered by archaeology. One of the most overlooked mysteries at Puente Tablas concerns urban organization, as excavations indicate that residential zones, public areas, defensive structures and ritual spaces were not randomly distributed, but instead formed an organized urban landscape. This challenges older assumptions about Iberian settlements, since for decades many scholars viewed pre-Roman Iberian communities as relatively simple compared with later Roman cities, yet Puente Tablas suggests otherwise by demonstrating evidence of planning, coordination, and long-term development. Roads connect key areas efficiently, important buildings occupy strategic locations, and public and sacred spaces appear intentionally separated, principles that modern urban planners would immediately recognize. Yet no surviving documents explain how ancient planners made these decisions, leaving the city itself as the only surviving blueprint. What do you think was the true secret behind Puente Tablas' Solar Gate? Generations of astronomical observation, a lost surveying technique, or a forgotten scientific tradition? Share your theory in the comments below. Sudak Fortress is a medieval giant standing on a volcanic hill above the Black Sea coast of Crimea. More than 6 centuries after its construction, its walls still dominate the landscape. Yet the greatest mystery is not the fortress itself. It is how medieval engineers, working without modern surveying instruments, cranes, or scientific materials laboratories, created a defensive system so durable that large portions remain standing today. The fortress was never truly lost. Historical records from Genoese merchants described Sudak as one of the most important trading and military centres of the northern Black Sea. Archaeological investigations beginning in the 19th century and continuing through the 20th and 21st centuries reveal the complex engineering hidden within its walls, towers, water systems, and construction materials. Sudak Fortress occupies a volcanic rock formation, rising approximately 157 meters above sea level. The position appears almost perfectly engineered by nature itself. Steep cliffs protect 3 sides of the hill, leaving only a limited approach for attackers. Military historians often compare strategic locations like Sudak to famous strongholds such as Masada or Crac de Chevalier. Yet Sudak possessed an additional advantage. It overlooked major maritime trade routes connecting the Byzantine Empire, the Caucasus, Central Asia, and the Mediterranean. What remains unclear is how medieval surveyors evaluated the site so effectively. Without aerial photography, satellite imagery, or topographic mapping, they identified a location that maximized visibility, controlled trade routes, and minimized defensive vulnerabilities. Modern geographic information system analysis demonstrates that observers from the fortress could monitor vast sections of the surrounding coastline and see approaches. Such strategic optimization suggests a level of geographic knowledge far beyond what many people associate with the medieval period. Most people imagine a fortress as a single wall surrounding a settlement. Sudak was something entirely different. The fortress was organized into multiple defensive zones. Attackers who breached the outer walls still faced additional layers of fortification. The system functioned much like a modern defense-in-depth strategy, forcing enemies to fight uphill through successive barriers. The outer defensive circuit stretched for nearly 2 kilometers and incorporated more than a dozen towers. Each tower was positioned to support neighboring towers through overlapping fields of fire. Archers and crossbowmen could cover areas that would otherwise become vulnerable blind spots. Computer simulations performed on medieval fortifications show that overlapping defensive coverage dramatically increases survival rates during sieges. Yet the exact methods used by Genoese engineers to calculate these relationships remain unknown. There are no surviving blueprints. There are no surviving engineering manuals. The fortress itself is the only surviving evidence of the calculations. One of the least discussed mysteries involves measurement. The walls follow the irregular contours of the mountain while maintaining structural stability over long distances. Achieving this required accurate surveying. Modern engineers use laser scanners capable of measuring distances to within millimeters. Medieval builders relied on ropes, plumb lines, wooden levels, and geometric principles inherited from Roman and Byzantine traditions. The question is not whether these tools existed. The question is how such simple instruments produced results accurate enough to construct a fortress across steep volcanic terrain. Archaeologists studying medieval fortifications have repeatedly found evidence that builders possessed practical geometric knowledge far more sophisticated than previously assumed. Similar mysteries surround the construction of Carcassonne, the walls of Theodosian walls, and the mountain fortresses of the Crusader states. Sudak belongs to this same category of engineering puzzles. Water determines whether a fortress survives a siege. Food can be rationed, weapons can be repaired. But without water, even the strongest fortress eventually falls. Sudak sits on a rocky hill with limited natural freshwater resources. Historical records and archaeological investigations indicate the existence of large storage cisterns designed to collect and preserve water supplies. The engineering challenge was enormous. The Black Sea region experiences seasonal fluctuations in rainfall. During prolonged sieges, thousands of soldiers, civilians, and animals could require water every day. A single person typically requires at least 2 to 3 liters of drinking water daily under normal conditions. During military operations, requirements increase significantly. This means a garrison of only 1,000 individuals could consume several thousand liters every day. Researchers still debate the full capacity of Sudak's water storage network. Some believe extensive rainwater harvesting systems supplemented local springs. Others argue that additional supply routes may have existed outside the visible archaeological record. Whatever the answer, the fortress could not have functioned without sophisticated hydraulic planning. Perhaps the most fascinating engineering mystery of Sudak Fortress lies within the walls themselves. Many sections of the fortress were constructed during the Genoese period in the 14th and 15th centuries. More than 600 years later, substantial portions remained standing despite earthquakes, warfare, coastal weathering, temperature fluctuations, and centuries of neglect. From a materials science perspective, this is extraordinary. Modern concrete structures often require major maintenance after only a few decades. Steel reinforcement can corrode. Freeze-thaw cycles can crack masonry. Salt carried by sea winds can gradually destroy building materials. Yet Sudak continues to endure. The fortress was primarily constructed using local limestone and sandstone, bonded with lime mortar. At first glance, this appears simple. However, scientific studies of historical mortars across the Mediterranean have revealed surprising complexity. Many medieval builders mixed crushed ceramics, brick fragments, volcanic materials, and other additives into lime mortar. These ingredients could trigger chemical reactions similar to those found in Roman hydraulic concrete. Microscopic analysis of ancient mortars from Roman harbours has shown that certain mineral crystals continue strengthening structures centuries after construction. Researchers have discovered rare calcium aluminum silicate compounds that contribute to remarkable durability. Could similar processes have occurred within the walls of Sudak? Some material analyses suggest that medieval builders understood far more about mortar performance than written records indicate. The exact recipes, however, were rarely documented. Construction knowledge was often transmitted through apprenticeship rather than books. When master builders died, portions of their expertise disappeared with them. This pattern appears repeatedly throughout history. Roman concrete remains durable after nearly 2,000 years. The mortar used in parts of the Great Wall of China incorporated sticky rice compounds that improved strength. Medieval cathedral builders created structures that have survived for centuries despite constant environmental stress. Sudak Fortress may represent another example of lost materials technology. Scientists can analyze surviving samples, identify mineral compositions, and model chemical reactions. Yet, reconstructing the complete manufacturing process remains difficult because the human knowledge behind the materials has vanished. The walls still stand, the builders' methods remain partly hidden. Construction on Sudak's scale required an immense logistical operation. The fortress covers roughly 30 hectares and includes massive walls, towers, gates, defensive platforms, and internal structures. Every stone had to be quarried. Every stone had to be transported uphill. Every stone had to be positioned precisely. Today, cranes can lift dozens of tons with ease. Medieval builders relied on human labor, animal power, wooden scaffolding, pulleys, and lifting devices derived from ancient engineering traditions. Archaeologists estimate that large fortification projects often required hundreds or even thousands of workers operating over decades. Yet many questions remain unanswered. How was labor organized? How were materials supplied consistently? How were construction schedules coordinated? The fortress preserves the result, but not the process. Along the Red Sea escarpment, on a wind-exposed plateau more than 2,600 meters above sea level, Quahito at first appears to be a modest cluster of ruins. But beneath that simplicity lies a contradiction. Here, in an environment defined by water scarcity, thermal stress, and erosion, ancient builders created a settlement that not only endured, but operated with a level of engineering logic comparable to far more advanced civilizations. The most unsettling mystery is not what was built, but how every part of the system seems to solve problems with an efficiency that should not have been possible with the tools and knowledge of its time. Although local populations had long known of the ruins, Quahito entered formal archaeological awareness in the early 20th century, during surveys of the Eritrean highlands conducted under Italian colonial administration. Subsequent expeditions throughout the 20th century mapped the plateau, revealing an extensive network of terraces, reservoirs, temples, and domestic structures spread across several square kilometers. Artifacts recovered, including inscriptions in the South Arabian script and architectural parallels, linked the site to the Kingdom of Aksum, a major trading power between roughly the 1st and 7th centuries CE. Yet even with this cultural attribution, the technological coherence of Quahito remained unexplained. Excavations produced fragments of a civilization but not the blueprint behind it. The defining constraint of Quahito is water. The plateau lacks any permanent river, and modern rainfall averages between approximately 300 and 500 millimeters annually, highly seasonal and unreliable. Yet archaeological evidence indicates a settlement capable of supporting a substantial population. At the center of this paradox stands the Saphira Dam, an ancient structure designed to capture and store runoff from rare rain events. Combined with rock-cut cisterns and channel systems, the plateau forms an integrated hydraulic network. Estimates suggest that even a modest reservoir capacity of several thousand cubic meters could sustain hundreds, possibly thousands of inhabitants if managed efficiently. This implies not only construction capability, but hydrological foresight understanding runoff patterns, evaporation rates, and storage efficiency. Comparatively, Roman cistern systems such as those in North Africa relied on similar principles, but were typically supported by formalized surveying tools, standardized measurements, and written engineering traditions. At Quahito, no such documentation has been found. The system exists, functions logically, yet lacks an identifiable knowledge framework. The architecture of Quahito is dominated by dry stone masonry, carefully shaped blocks assembled without mortar. This technique is widespread in ancient construction, from Mediterranean terraces to Andean walls. However, the execution here introduces a critical anomaly. Stone blocks are fitted with remarkable precision, reducing voids and enhancing structural stability. In many locations, walls remain standing after nearly 2,000 years of exposure. The precision suggests controlled shaping, yet there is limited evidence of advanced metal tools typically associated with such work. From an engineering standpoint, such tight-fitting construction reduces internal stress distribution and increases resistance to lateral forces, including wind and minor seismic activity. But this raises a question of intent. In a resource-limited environment, why invest labor into achieving a level of precision beyond what is structurally necessary? This pattern echoes other ancient sites such as Inca stonework at Machu Picchu, where precision appears to exceed immediate functional requirements. In both cases, the construction implies a deeper understanding of material behavior than the archaeological record clearly supports. The most difficult mystery to reconcile is not structural design, but material survival. High-altitude plateau environments impose extreme stress on stone construction. Daily temperature fluctuations can exceed 20 degrees Celsius, producing cycles of thermal expansion and contraction. Over time, this leads to microfracturing, displacement, and eventual collapse, particularly in dry masonry systems lacking binding agents. Wind erosion further accelerates degradation, especially in exposed terrains such as Cuajito. Under such conditions, many ancient dry stone structures elsewhere show significant collapse within centuries. Yet at Cuajito, numerous walls and terraces remain partially intact after nearly 2 millennia. Stones show limited displacement. Structural lines remain coherent. In some cases, surface textures suggest deliberate shaping or finishing that may influence weather resistance. From a material science perspective, durability at this scale implies one or more of the following: careful selection of lithology, choosing stone types with low porosity and high muqawmet to thermal stress; optimization of block geometry, minimizing stress concentrations and improving load distribution; possible surface treatment, whether through polishing, heat exposure, or other unknown methods that alter erosion rates. The absence of binding material makes this even more striking. Stability emerges purely from geometry, mass, and friction. When compared to other ancient sites exposed to similar climates such as dry stone settlements in the Levant or North Africa, Cuajito's preservation appears disproportionate. It does not simply survive. It persists beyond what environmental models would predict. Beyond individual structures, the plateau reveals signs of coordinated planning. Terraces are aligned to maximize land use and possibly control runoff. Pathways connect elevated and lower zones efficiently. Architectural clusters suggest zoning: domestic, ceremonial, and possibly administrative. Such organization implies a systemic approach to settlement design. Yet, unlike Roman or Mesopotamian contexts, there is no surviving body of written engineering instructions, measurement systems, or architectural treatises associated with the site. This absence creates a paradox. The physical evidence indicates planning. The historical record does not preserve the process. Cuajito is often interpreted as part of the broader Aksumite world, a civilization known for trade networks extending across the Red Sea and into the Mediterranean. However, even within that context, the plateau stands apart. Its solutions are highly localized, tailored to a specific environmental constraint. Its engineering is efficient, but not visibly derived from known traditions. And most importantly, its knowledge system, whatever produced it, has left almost no trace. There is no gradual progression visible in the archaeological layers that leads clearly to this level of integration. Instead, the system appears already functional, already optimized. So how did a system this coherent exist, without leaving behind the knowledge that made it possible? What do you think explains Cuajito's engineering lost knowledge, overlooked science, or something else entirely? Share your thoughts in the comments below. In Iksan, South Korea, the ruins of Wangung-ri appear deceptively simple, yet beneath a quiet landscape of stone foundations and scattered walls lies evidence of a city-scale engineering project built more than 13 centuries ago. Archaeologists can measure its dimensions, map its structures, and analyze its materials, but some of the most important questions remain unanswered. How did ancient builders achieve such precise geometric planning, such advanced water management, and such large-scale landscape modification with technologies that have largely disappeared from history? The site first attracted archaeological attention during the 20th century, but large-scale excavations revealed something unexpected, as beneath centuries of accumulated soil were the remains of what many scholars believe was a royal palace complex of the Baekje kingdom, later transformed into a Buddhist center. Excavations uncovered walls, drainage systems, building foundations, workshops, roads, and the famous 5-story stone pagoda, and together they revealed a settlement planned on a scale far greater than previously imagined. One of the most remarkable aspects of Wangung-ri is that it does not appear to have grown gradually like many ancient settlements, but instead displays signs of deliberate planning from the beginning. Archaeological surveys indicate that major structures were arranged along carefully controlled axes, with buildings, courtyards, walls, and access routes organized according to a coherent spatial plan, raising a difficult question because planning is easy on paper, while implementing it across an uneven landscape is far more challenging. Modern engineers rely on laser surveying equipment, GPS systems, satellite positioning, digital terrain models, and precise measurement tools. Yet 7th century builders possessed none of these technologies, and still the archaeological layout suggests that someone understood how to impose geometric order across a large area with surprising consistency. This challenge becomes even more intriguing when compared with other ancient plan centers such as Marzabotto in Italy, Teotihuacan in Mexico, and Chang'an in Tang, China, where urban planning reached extraordinary levels of sophistication, placing Wangung-ri within the same conversation despite being far less famous. The mystery is not whether ancient people could create geometric cities as many clearly did, but how the surveyors of Wangung-ri maintained such accuracy without leaving behind any surviving technical manuals explaining their methods. The most fascinating technological puzzle at Wangung-ri concerns geometry itself, as when archaeologists reconstruct the site, they encounter repeated evidence of intentional alignment, with structural foundations corresponding with major axes, walls following consistent orientations, and important buildings positioned according to a broader architectural scheme rather than simple convenience. Creating such a plan required more than basic construction skills, as it required precise measurement, and even today surveyors must establish reference points, calculate distances, compensate for terrain irregularities, and maintain consistency over long distances, where small errors accumulate rapidly, and even a mistake of 1 degree can produce substantial displacement across hundreds of meters. Yet Wangung-ri demonstrates a level of geometric control suggesting that its builders possessed methods capable of minimizing such errors, although how they achieved this remains uncertain. Some researchers suggest the use of astronomical observations, as ancient civilizations frequently used the sun, stars, and shadow measurements to establish orientation, with Egyptian pyramid builders and Chinese astronomers demonstrating similar capabilities, while others argue that practical surveying methods such as rope measurements, sighting poles, water levels, and standardized units may have been sufficient. Experimental archaeology shows that skilled surveyors using simple equipment can achieve remarkable precision. but reproducing an entire planned complex remains far more difficult than constructing a single building, leaving the unresolved question not whether geometric precision was possible, but how consistently it was maintained throughout an entire architectural system. Another mystery lies beneath the visible ruins, as geological investigations suggest that large portions of the site were artificially modified before construction began, with builders leveling terrain, redistributing soil, stabilizing foundations, and creating construction platforms suitable for major buildings. This process would have required enormous labor, and while modern earth-moving projects depend on excavators, trucks, surveying instruments, and engineering calculations, ancient workers relied primarily on human labor and simple tools. Archaeologists estimate that large ancient construction projects often required moving tens of thousands of cubic meters of earth, and even modest elevation adjustments could involve transporting thousands of tons of material, making the challenge not merely moving soil but ensuring long-term stability. Poorly compacted fill settles over time, causing foundations to crack, walls to deform and drainage systems to fail, yet much of Wangungri remained structurally stable long enough to support significant architecture, suggesting an understanding of soil behavior that is difficult to reconstruct from surviving evidence alone. Perhaps the most impressive engineering achievement at the site is its drainage network, as excavations uncovered carefully designed channels capable of directing water away from sensitive structures, addressing a problem that plagued many ancient cities struggling with flooding, erosion, and foundation instability. At Wangungri, drainage appears integrated into the overall design rather than added later as a correction, with channels exhibiting controlled gradients that suggest deliberate planning, allowing water to be directed through a system that minimized damage while protecting key areas of the complex. Hydrology is one of the most underestimated aspects of ancient engineering, as a poorly designed drainage system can destroy decades of construction, while a successful one can preserve structures for centuries, as seen in comparable achievements at Machu Picchu and Angkor. Although Wangungri operated on a smaller scale, its engineering principles appear surprisingly sophisticated, leaving the mystery of how ancient builders determined optimal gradients and flow characteristics without modern mathematical modeling. The famous 5-story pagoda presents another engineering puzzle, as although constructed from stone, the structure imitates architectural forms originally developed for timber buildings, requiring more than decorative imitation, but a translation of an entire construction philosophy from one material to another. Wood and stone behave very differently, with wood bending under stress while stone resists compression but fractures under tension, meaning structural solutions effective for timber may fail when reproduced in stone. Yet the pagoda demonstrates that Baekje craftsmen successfully adapted wooden architectural concepts into a durable stone form, with remarkable precision in masonry as individual blocks were shaped to create proportions and visual effects associated with timber architecture. This required not only craftsmanship but also an intuitive understanding of structural mechanics, and although the builders may never have written mathematical equations describing load distribution, the survival of the monuments suggests that they understood these principles through experience and accumulated knowledge. What is your theory behind Wangungri's remarkable precision? Let us know in the comments below. In the rolling hills of southern Corsica, France, stands a collection of stone warriors that have silently watched the Mediterranean for nearly 4,000 years. Known today as the Filitosa statue menhirs, these prehistoric monuments appear at first glance to be simple standing stones, but the closer archaeologists examined them, the more unsettling the questions became. They are carved from some of the hardest granite on the island, sculpted into unmistakably human forms with carefully balanced proportions, detailed facial features, and even engraved Bronze Age weapons. Even more astonishing, they seem to have been created with almost no evidence of mistakes. There are virtually no abandoned sculptures, no unfinished experiments, and almost no traces revealing how prehistoric craftsmen learned to master such difficult stone. The modern story of Filitosa began in 1946, when local landowner Charles-Antoine Cesari noticed unusual carved stones scattered across his property. Formal excavations started in the mid-1950s under archaeologist Roger Grosjean, revealing not only dozens of statue menhirs but also circular stone monuments, defensive walls, dwellings, and evidence of continuous occupation stretching from roughly 3300 BC to the Bronze Age. Radiocarbon dating, pottery analysis, and comparisons with nearby Corsican sites gradually established Filitosa as one of the most important prehistoric ceremonial landscapes in the Western Mediterranean. Yet every new discovery only deepened the mystery surrounding the technology of the people who built it. The first puzzle begins with the stone itself. Nearly every statue at Filitosa was carved from local granite, a rock dominated by quartz and feldspar that measures approximately 6 to 7 on the Mohs hardness scale. Granite remains one of the most demanding materials even for modern stoneworkers. Today it is commonly cut using diamond-coated saws, pneumatic chisels, and computer-guided equipment. 4,000 years ago, however, the inhabitants of Corsica possessed neither iron nor steel. Their primary tools were fashioned from harder stone, antler, wood, and eventually limited amounts of bronze, which is significantly softer than granite itself. Experimental archaeology has repeatedly demonstrated that shaping granite with such tools is possible, but painfully slow. Producing a smooth surface only a few square centimeters in size can require many hours of repetitive pecking, grinding with quartz sand and polishing. Yet the sculptors at Filitosa transformed multi-ton blocks into remarkably refined human figures. Many of the statues display carefully proportioned faces. Their noses emerge in raised relief rather than being carved inward. The eye sockets remain symmetrical while long swords and daggers are engraved with straight, confident lines running down the center of the body. These are not random decorative scratches. They reveal deliberate planning and a surprisingly consistent artistic language maintained across multiple generations. Some statues stand more than 2.5 meters tall and weigh several tons, making every carving decision effectively irreversible. Remove too much stone from one side, and the entire sculpture would lose its balance forever. This leads directly to perhaps the most astonishing mystery at Filitosa. The sculptures show almost no evidence of trial and error. Modern sculptors often begin with clay models, plaster casts, sketches, grids, or digital 3-dimensional scans before touching the final block of stone. Ancient Egyptian sculptors frequently left unfinished statues behind, allowing archaeologists to reconstruct every stage of production. The colossal statues on Easter Island preserve abandoned examples still attached to the quarry. Even Renaissance masters such as Michelangelo left partially completed works that reveal corrections made during carving. Filitosa offers almost none of these clues. Archaeologists have identified surprisingly few unfinished statue menhirs. Almost no abandoned practice pieces have been discovered. The completed figures exhibit remarkably consistent proportions, despite likely being produced over centuries rather than decades. Facial dimensions, shoulder widths, and weapon placement follow similar visual rules, even though individual craftsmen almost certainly differed in experience. Such uniformity strongly suggests that these prehistoric sculptors were following an established system rather than improvising each monument independently. What that system actually looked like remains unknown. Did they first draw outlines directly onto the granite using charcoal or red ochre? Did they stretch cords across the stone to establish a central axis before carving? Perhaps wooden measuring frames ensured every face maintained similar proportions. Some researchers have even proposed that experienced master sculptors trained apprentices through highly standardized oral traditions, allowing complex geometric knowledge to survive without written language. None of these possibilities has been confirmed because wood, leather, fiber ropes and pigments rarely survive after 4 millennia in the Corsican climate. The absence of obvious mistakes becomes even stranger when viewed from an engineering perspective. Granite cannot easily be repaired. Unlike wood, it cannot simply be filled or reshaped after major errors. One misplaced blow can create fractures extending deep inside the block. Those hidden cracks may remain invisible until the statue eventually breaks under its own weight. Yet the surviving monuments display surprisingly few catastrophic failures attributable to carving accidents. Either unsuccessful statues were systematically destroyed and removed, leaving almost no archaeological trace, or these craftsmen possessed an astonishing level of confidence before they ever struck the stone. Transporting the finished monuments presented another challenge that archaeology has yet to answer completely. Many statue menhirs weigh between 2 and 5 metric tons. Although the granite often originated relatively close to the site, even moving such weights across uneven Corsican terrain would have demanded careful planning. There is no evidence that these prehistoric communities possessed wheeled vehicles capable of transporting massive stones. Horses had not yet become established draft animals on the island, and no preserved roads specifically designed for megalith transport had been identified. The most widely accepted theories involve wooden sledges sliding across lubricated tracks, log rollers, earthen ramps, or large coordinated teams pulling with plant fiber ropes. Experimental reconstructions elsewhere demonstrate that dozens of people can indeed move stones, weighing several tons using only prehistoric technology. The problem is that no direct archaeological evidence confirms exactly which technique was employed at Filitosa. Once transported, each monument still had to be raised into an upright position. This required excavating a foundation pit, controlling the center of gravity during lifting, stabilizing the base, and carefully backfilling the surrounding soil. Many of these stones have remained standing despite thousands of years of seasonal rain, erosion, seismic activity, and powerful Mediterranean winds. Modern structural engineers recognize that long-term stability depends heavily on proper load distribution beneath the monument. Yet the prehistoric builders left no instructions explaining how they achieved this remarkable durability. Another remarkable feature lies in the engraved weapons covering several statues. Unlike simple stick figures, many Filitosa monuments depict recognizable Bronze Age swords, daggers, belts, and protective equipment. These carvings are not randomly placed. The weapons consistently occupy central positions aligned with the body's vertical axis. Their proportions resemble real weapons excavated elsewhere in Corsica and neighbouring Sardinia, providing valuable chronological evidence. The precision of these engravings demonstrates that the sculptors combined artistic ability with careful geometric planning, maintaining straight lines across uneven granite surfaces that naturally resist controlled carving. Near modern Eritrea on the shore of the Red Sea lies a forgotten city called Adulis. Today it appears as little more than scattered ruins buried beneath sand and stone. Yet, nearly 2,000 years ago, this port stood at the center of one of the largest trade networks on Earth. The greatest mystery is not that Adulis existed. The mystery is that one of the most important ports of the ancient world seems to have vanished almost completely, leaving behind questions that archaeology still cannot fully answer. European travellers recorded the ruins during the 19th century, while systematic archaeological excavations during the 20th century revealed monumental structures, imported ceramics, inscriptions, warehouses, and evidence of extensive international trade. What emerged was not a provincial settlement, but the remains of a sophisticated maritime hub connected to Rome, Arabia, India, and the Kingdom of Aksum. The most fascinating mystery surrounding Adulis is surprisingly simple. Where is the harbour? Ancient texts describe Adulis as one of the busiest ports in the Red Sea, and the first-century maritime guide known as the Periplus of the Erythraean Sea portrays it as a major commercial centre receiving ships from Egypt, Arabia, and India. Historical records indicate that ivory, rhinoceros horn, tortoiseshell, obsidian, gold, slaves, textiles, wine, olive oil, and manufactured goods all passed through the city. Yet, despite decades of archaeological investigation, researchers have never identified a harbour complex that matches the scale described by ancient sources, and this absence is difficult to explain. Large ports typically leave unmistakable signatures, as seen at Ostia near Rome, where archaeologists can still trace artificial basins, warehouses, breakwaters, and docking facilities, or at Alexandria, where submerged structures remain visible beneath the Mediterranean. Even ancient harbours damaged by earthquakes often preserve recognisable remains, but Adulis does not. Some scholars suggest that coastal changes over nearly 2 millennia may have altered the shoreline dramatically, with geological studies showing that sediment accumulation can shift coastlines by hundreds of metres over long periods, while in river-fed regions entire ports have disappeared beneath mud deposits. Others propose that tectonic activity, sea level fluctuations or erosion, may have buried or destroyed critical harbour infrastructure. The problem is that none of these explanations completely solves the puzzle, because if Adulis handled the volume of trade described by ancient writers, its maritime infrastructure should have been substantial, yet the physical evidence remains frustratingly limited. It is as if the most important component of the city simply vanished. The scale of Adulis becomes even more remarkable when viewed through the lens of geography, as the distance between Adulis and Alexandria exceeds 2,000 kilometers, and the distance to Western India is even greater. Yet despite these enormous separations, goods traveled between these regions with surprising regularity. Archaeologists have recovered Roman amphorae, Mediterranean glassware, South Arabian ceramics, Indian trade goods, and Aksumite artifacts from the site, with each object representing part of a logistical chain spanning thousands of kilometers. Modern shipping depends on satellites, digital navigation, weather forecasting, and detailed charts, but ancient sailors possessed none of these tools, and yet trade moved efficiently enough to support an international economy. Researchers know that Red Sea navigators exploited monsoon wind systems crossing the Arabian Sea, with seasonal winds allowing ships to travel between Arabia, East Africa, and India with far greater speed than previously believed, although understanding monsoons is only part of the equation. Captains still needed accurate navigation, knowledge of reefs, freshwater sources, coastal landmarks, seasonal hazards, and emergency anchorages, and the cumulative expertise required for such voyages may have represented one of the most sophisticated bodies of maritime knowledge in the ancient world. Unfortunately, almost none of this knowledge survives in written form, as the ships are gone, the manuals are gone, the navigators are gone, and only fragments of their network remain. Another puzzle concerns the technical organisation required to keep Adulis functioning, because trade on the scale described by historical records cannot operate through improvisation alone. Every arriving vessel required cargo handling, storage, taxation, distribution, security, maintenance, and scheduling, and goods arriving from one continent needed to be transferred to merchants bound for another, implying a degree of administrative coordination that resembles later commercial centres. Yet the archaeological record contains surprisingly little documentation, and unlike Egypt, Rome, or Mesopotamia, Adulis has not yielded vast archives explaining how its economy functioned. Researchers can observe the results of a complex system without fully understanding the mechanisms behind it, making the situation resemble discovering a modern airport after all records have disappeared, where runways remain, buildings remain, infrastructure remains, but the operating manual is missing. The success of Adulis depended on another engineering challenge that remains only partially understood: water. The surrounding region experiences arid conditions, and a major port requires enormous quantities of fresh water, as residents need water, visiting sailors need water, animals require water, and workshops and industrial activities require water. Excavations have revealed reservoirs, storage facilities, and hydraulic features suggesting deliberate water management, yet archaeologists have not yet reconstructed the entire system, leaving questions such as how much water the city could store, how seasonal variation was managed, and what mechanisms prevented shortages during periods of drought. Ancient cities such as Petra, Machu Picchu, and Carthage became famous for hydraulic engineering because substantial portions of their system survive. But Adulis presents a different challenge because enough evidence exists to prove sophisticated water management, while not enough survives to reveal the complete design. One of the strangest mysteries concerns shipbuilding itself, as a port of Adulis's importance should have required continuous vessel maintenance. Given that ships operating in saltwater environments deteriorate rapidly, hulls need repairs, masts require replacement, and ropes wear out. Large-scale maritime commerce depends upon infrastructure, yet definitive shipyards remain elusive, and archaeologists have found evidence of trade but comparatively little evidence of the facilities needed to sustain that trade. This creates a paradox in which the commercial activity is visible while the supporting technology is largely invisible. Part of the explanation may be preservation bias, since wooden structures decay rapidly in coastal environments, and organic materials often disappear entirely after centuries of exposure. But nevertheless, the scarcity of direct evidence continues to surprise researchers. Comparison with other ancient centres highlights the uniqueness of Adulis. As Alexandria became famous for monumental harbour engineering and the lighthouse of Pharos, Ostia became known for its massive artificial basins serving Rome. The Nabatean city of Petra demonstrated extraordinary water management in an arid landscape, and the ports of the Indus and Persian Gulf reveal extensive maritime infrastructure. Adulis differs because much of its importance is known from its connections rather than its surviving monuments, and its influence appears larger than its archaeological footprint. This mismatch between historical significance and surviving evidence is one reason the site remains so intriguing, as the city seems to have played a critical role in global trade, while leaving behind fewer answers than expected. The greatest mystery is not how Adulis functioned, but why it vanished. By the 7th century, shifting powers, trade routes, and conflicts were reshaping the Red Sea region. While historians link its decline to these broader changes, no clear explanation exists. Unlike most ports that decline gradually, Adulis seems to have disappeared quickly, leaving little trace. For a city that once connected Africa, Arabia, and Asia, its end remains unclear. Was the harbour destroyed, buried, or simply not yet found? Share your thoughts in the comments below. Hidden beneath the quiet countryside near Évora, Portugal, stands one of the largest Stone Age monuments ever built in Europe. A tomb whose greatest mystery is not why it was constructed, but how people more than 6,000 years ago managed to build it at all. ****. The monument, now known as Anta Grande do Zambujeiro, was first brought to archaeological attention in the 1960s after local farming activities exposed portions of its enormous stone chamber. Excavations led by Portuguese archaeologist Georg Leisner revealed an astonishing structure buried beneath centuries of collapsed earth. Radiocarbon dating of artifacts recovered from the site places its construction between approximately 4000 and 3500 BC, making it significantly older than Stonehenge and nearly contemporary with the earliest phases of the Egyptian pyramids. Hidden beneath a massive earthen mound was one of the largest dolmens ever discovered on the Iberian Peninsula, its chamber formed by 7 gigantic granite slabs supporting an equally enormous capstone. Thousands of years of erosion had concealed the monument, but its remarkable engineering survived almost intact. Standing inside the chamber today, the first question becomes unavoidable. How did Neolithic builders raise stones weighing well over 20 tons without iron tools, without cranes, without pulleys, and possibly before the widespread use of the wheel? Each upright orthostat rises nearly 7 meters high, with individual blocks estimated to weigh between 20 and 30 tons. Even transporting such stones would have represented a major engineering challenge, yet lifting them into a perfectly stable vertical position presents an even greater mystery. Modern cranes solve this problem through hydraulics, steel cables, and carefully calculated lifting points. The builders of Anta Grande possessed none of these technologies. They worked with polished stone axes, wooden tools, plant fiber ropes, and human labor. Yet somehow they achieved a result that has remained standing for over 6 millennia. Experimental archaeologists have proposed several possible construction methods. One suggests that the builders dug deep foundation pits, tilted the stones into position, using enormous wooden levers, and then gradually filled the holes around the base to secure them. Another proposes long earthen ramps that allow the stones to be dragged upward before being lowered into prepared sockets. Others suggest elaborate timber frameworks acting as primitive lifting systems. Every hypothesis can reproduce part of the process, but none explains the entire construction sequence convincingly. The greatest obstacle is not simply moving one stone, it is placing 7 enormous slabs so accurately that they could later support a single capstone weighing perhaps 15 to 20 tons without collapsing during construction. The capstone itself introduces another engineering puzzle. Raising such a massive block to a height approaching 6 meters would require extraordinary coordination. If an earthen ramp was used, calculations suggest that the builders may have needed to move thousands of cubic meters of soil, creating a temporary artificial hill much larger than the monument itself. Once construction finished, nearly all of that earth would have needed to be removed again, leaving surprisingly little archaeological evidence behind. If wooden lifting systems were employed instead, they would have been subjected to enormous compressive and tensile forces. Fresh oak timbers can support considerable loads, but maintaining stability while positioning a 20-ton stone above standing orthostats would have demanded an understanding of balance and structural behavior far beyond what is traditionally associated with Neolithic farming communities. What makes the monument even more remarkable is the precision with which those giant stones were arranged. At first glance, the chamber appears irregular because each granite slab preserves its natural shape. Yet detailed surveys reveal that the builders created a surprisingly symmetrical polygonal interior. The spacing between orthostats distributes the capstone's weight efficiently across multiple support points, reducing stress concentrations that could have fractured individual stones. Modern structural engineers recognize similar principles in load distribution used in masonry architecture. Whether the builders understood these concepts mathematically or acquired them through generations of accumulated practical experience remains unknown. Either explanation implies a sophisticated body of engineering knowledge that has left almost no written record. The origin of the stones presents another unanswered question. Geological analysis indicates that the granite likely came from nearby outcrops rather than distant quarries, but nearby still meant transporting blocks weighing dozens of tons across uneven terrain. Even over distances of only 1 or 2 kilometers, the task becomes immense. Experiments performed on comparable megalithic monuments suggest that moving a 25-ton stone on wooden sledges might require well over 100 people pulling simultaneously, depending on terrain and lubrication. Some researchers estimate that wet clay, animal fat, or water could have reduced friction, while others argue for carefully prepared timber trackways. Yet, around Antegrande do Zambujeiro, archaeologists have discovered little physical evidence of transportation routes. The engineering solution vanished long before history was written. Equally fascinating is the selection of the stones themselves. Granite is an extremely durable material, but not every block is suitable for construction. Internal fractures invisible from the surface can cause catastrophic failure under heavy loads. Modern engineers identify such weaknesses using ultrasonic testing, laser scanning, and stress analysis. Neolithic builders possessed none of these technologies. Nevertheless, the stones chosen for Antegrande have survived thousands of years of weathering earthquakes, seasonal temperature changes, and the tremendous pressure exerted by the capstone. Whether this success resulted from remarkable observational skill, generations of quarrying experience, or techniques that have since been forgotten remains impossible to determine. The monument's long entrance corridor raises further questions about planning. Extending roughly 13 meters from the central chamber, the passage is far more than a simple access route. Its walls maintain an impressive consistency despite being constructed from irregular megaliths. Building such a corridor required establishing a stable axis before the chamber itself was completed, meaning the entire monument must have existed as a carefully planned design rather than an improvised collection of stones. Surveying without modern instruments is difficult even on small construction projects. Creating accurate alignments across large megalithic structures demands careful observation, repeated measurement, and standardized methods that archaeologists can only partially reconstruct. Some researchers have suggested that the corridor's orientation may also possess astronomical significance. Across Atlantic Europe, many megalithic tombs appear aligned towards sunrise during specific times of the year, particularly around solstices or equinoxes. Similar alignments are known at monuments such as Newgrange in Ireland, where sunlight penetrates deep into the burial chamber during the winter solstice. At Antegrande do Zambujeiro, however, the evidence remains inconclusive. Thousands of years of structural collapse, slight shifts in stone positions, and erosion of the surrounding mound complicate precise measurements. If the alignment was intentional, the builders would have needed decades of careful observation to determine recurring solar positions before construction even began. If it was coincidental, it is an extraordinary coincidence shared by many other megalithic monuments across Western Europe. Afrasiab is the ancient core of Samarkand, a site whose buried layers reveal a level of technical sophistication that does not fully align with conventional timelines of urban development in Central Asia. What emerges from its ruins is not just a lost city, but a system, engineered with precision, maintained over centuries, and ultimately erased in a way that still raises unresolved questions. The discovery of Afrasiab was not a single breakthrough moment, but a gradual unveiling. By the late 19th century, Russian archaeologists began systematic excavations on the northeastern edge of modern Samarkand, uncovering walls, pottery, and urban remains buried beneath layers of earth. What initially appeared to be scattered ruins soon revealed a continuous settlement history, stretching back to approximately the 8th century BCE. Stratigraphic analysis showed multiple occupation layers, in some areas exceeding several meters in depth. Each layer represented a different phase of construction, destruction, and rebuilding, suggesting not just longevity, but continuity of technical knowledge. Unlike many ancient sites that show abrupt cultural breaks, Afrasiab appeared to evolve, refine, and adapt over time. Afrasiab existed in a semi-arid zone, where sustaining a large population required more than access to water, it required control. Excavations revealed an intricate network of canals, reservoirs, and distribution systems, many of which were aligned with subtle elevation gradients. Some channels maintained a consistent slope over long distances, minimizing stagnation and maximizing flow efficiency. Modern hydraulic engineering recognizes that even a gradient deviation of less than 1% can significantly alter water velocity and sediment buildup. The fact that ancient engineers achieved such consistency without modern instruments suggests either highly refined surveying techniques or long-term empirical calibration. Comparisons with other ancient hydraulic systems, such as those in Petra or the Karnat systems of Persia, show parallels in concept, but Afrasiab's integration into a dense urban grid appears unusually cohesive. This was not an add-on system, it was embedded into the city's design from the beginning. The layout of Afrasiab suggests more than organic growth. Defensive walls, administrative centers, residential clusters, and ceremonial spaces were arranged in a structured hierarchy. Roads connected directly to water distribution points, and population density appears to have been managed relative to resource access. Some alignments of streets and structures have been proposed to correspond with environmental factors such as prevailing winds or solar exposure. While these interpretations remain debated, the consistency of orientation across different construction phases indicates intentional planning. In comparison, many early urban centers, such as those in Mesopotamia, often show irregular expansion patterns, shaped by immediate needs rather than long-term planning. Afrasiab, by contrast, gives the impression of a city designed with foresight, as if its builders were working within a conceptual framework that has not been fully reconstructed. Among all discoveries, the Afrasiab murals stand as the most technically and conceptually unsettling. Dating to the 7th century CE, these wall paintings depict diplomatic scenes involving Sogdian rulers and foreign envoys from regions including China and Persia. At first glance, they appear to be historical artwork, but closer analysis reveals anomalies that challenge assumptions about ancient artistic capability. The pigments themselves are remarkably well preserved. After more than 13 centuries, many sections retain vivid blues, reds, and yellows, with minimal fading. Scientific analysis has identified mineral-based pigments such as lapis lazuli and iron oxides, but what remains unclear is the binding medium. The durability suggests the use of complex organic compounds or layered application techniques that enhanced adhesion and resistance to environmental degradation. In modern conservation science, preserving color stability over centuries requires precise control over pigment composition, substrate preparation, and environmental conditions. Yet the Afrasiab murals achieved this without controlled environments. Compared to Roman frescoes, many of which have degraded significantly over similar timescales, the Afrasiab paintings display an unusual resilience. Even more striking is the execution. The lines are consistently fine, with minimal variation in thickness, suggesting controlled application tools. Facial proportions remain stable across multiple figures, implying either measurement guidelines or advanced artistic training systems. The perspective, while not fully geometric in the Renaissance sense, shows an understanding of spatial layering and narrative sequencing. Microscopic analysis reveals layered paint application, where base tones were applied first, followed by finer detailing. This multi-stage process requires not only technical skill, but also planning each layer must anticipate the next. Errors would be difficult to correct, yet the murals show little evidence of major revisions. The question is not whether ancient artists were skilled. They clearly were. But whether the level of precision seen here implies tools or techniques that have not been preserved. No detailed records of brushes, measurement instruments, or pigment preparation methods have been definitively linked to the murals. What remains is the result, artwork that behaves, in terms of durability and consistency, closer to engineered material than simple paint. In this sense, the Afrasiab murals blur the boundary between art and technology. They represent a system of knowledge, chemical, procedural, and aesthetic that appears fully developed yet largely undocumented. Afrasiab's fortifications evolved over time, becoming thicker and more complex in response to external threats. Some sections include angled bastions and layered walls designed to absorb and redirect impact forces. This suggests an understanding of mechanical stress and attack dynamics. Comparatively, similar defensive adaptations can be observed in later medieval fortifications across Europe and the Middle East. However, the presence of such features in earlier phases at Afrasiab raises the possibility that these principles were understood and applied much earlier than commonly assumed. By the early 13th century, Afrasiab was largely abandoned following the Mongol invasions, yet archaeological evidence suggests that some systems may have already been failing. Sections of the water network show signs of blockage or disrepair. If the city depended on finely calibrated infrastructure, even minor disruptions could have triggered cascading failures. A breakdown in water supply would affect agriculture, sanitation, and population stability within a short time frame. This introduces a paradox. The same level of technical sophistication that allowed Afrasiab to thrive may also have made it vulnerable. Highly optimized systems often lack redundancy. When they fail, they do so rapidly and completely. If the Afrasiab murals required knowledge that rivals controlled material science, how much ancient technology have we already lost without ever realizing it existed? Few places make the past feel deliberately hidden rather than distant. Kudakalu Parambu is one of them. At first glance, it looks almost absurd. Dozens of massive stone structures shaped like umbrellas or mushrooms, each consisting of a single vertical shaft topped by a wide circular capstone. No walls, no chambers, no obvious engineering complexity. And yet, the longer you look, the less sense it makes. Because each of these stones weighs tons, each has remained standing for over 2,000 years. And no written record explains who built them, how they were constructed, or why such a strange design was chosen in the first place. The name itself is deceptively simple. Kudakalu translates to umbrella stones, a term that describes their appearance but reveals nothing about their purpose. The site, located in the Thrissur district of Kerala in southern India, belongs to the broader tradition of Iron Age South India, a cultural horizon stretching across peninsular India between roughly 1000 BCE and 300 CE. Across this region, archaeologists have documented dolmens, stone circles, cairns, and burial chambers. But Kudakalu Parambu does not fit comfortably into any of these categories. It is familiar enough to be recognized as part of a megalithic tradition, yet distinct enough to resist easy classification. The site first entered formal archaeological awareness during surveys conducted in the 20th century, when researchers began systematically cataloguing megalithic monuments across Kerala. What they found at Kudakalu Parambu was not a single structure, but a field of them. More than 60 stone monuments scattered across the landscape. Early interpretations were cautious. The assumption, based on parallels with other megalithic sites in India, was that these were burial markers. Excavations soon provided partial confirmation. Beneath several of the umbrella stones, archaeologists uncovered burial pits containing fragments of pottery, iron objects, and, in some cases, human remains. These findings aligned with known Iron Age funerary practices in the region, where the dead were often interred with grave goods. But the more excavations were conducted, the more the narrative began to fracture. Not every structure corresponded to a burial. Some revealed no human remains at all. Others showed signs of disturbance, reuse, or incomplete construction. The pattern was inconsistent. If these were graves, they didn't follow a standardized system. If they were markers, they were applied unevenly. And if they served a ritual function, that function left behind no clear material signature. Each excavation answered one question while introducing several more. The most unsettling discoveries were not the artifacts themselves, but the absences. No inscriptions, no symbolic carvings, no directional alignments that could be definitively linked to astronomical events. Unlike sites such as Stonehenge, where alignments with solstices and celestial cycles provide at least a partial framework for interpretation, Kudakalu Parambu offers no such clarity. It is a site that appears intentional in every aspect, yet refuses to communicate its intention. And then there is the construction. At a superficial level, the design is almost primitive. A single pillar-like shaft supporting a flat, disc-shaped stone above it. No joints, no interlocking systems, no visible reinforcements. But this simplicity is misleading, because when examined through the lens of physics and material constraints, the structure becomes far more complex than it appears. The stones used are primarily laterite, a material abundant in Kerala. When freshly quarried, laterite is relatively soft and can be cut with basic tools. However, once exposed to air, it undergoes a process of hardening, becoming significantly more durable over time. This characteristic may explain how the stones were shaped, but it does not explain how they were transported or erected. A typical capstone can weigh several tons. Moving such a mass without wheeled transport, draft animals capable of heavy hauling, or metal lifting tools presents a non-trivial engineering challenge. More importantly, the stability of the structure raises deeper questions. The contact area between the vertical shaft and the capstone is limited. There are no visible locking mechanisms, and yet many of these stones have remained upright for over 2 millennia, enduring monsoon rains, soil erosion, and seismic activity. This suggests an implicit understanding of load distribution and center of gravity. The builders may not have formalized these principles mathematically, but their practical application is undeniable. To put this into perspective, consider megalithic constructions elsewhere. At Stonehenge, large horizontal lintels are supported by multiple vertical stones, distributing weight across a broader base. In Korean dolmens, massive capstones rest on several supporting stones, creating a stable platform. Even in Egyptian architecture, weight is managed through redundancy and distribution of forces. Kudakalu Parambu, by contrast, relies on a single point of support. It is a minimal solution to a maximal problem. This raises an uncomfortable possibility, that the builders possessed a level of empirical engineering knowledge that we tend to underestimate. Not because it was advanced in a modern sense, but because it was precise in a way that leaves little margin for error. A misalignment of even a few degrees could destabilize the entire structure. And yet, Across dozens of monuments, the success rate is remarkably high. The question then becomes not just how these structures were built, but why they were built this way. If the goal was purely functional, to mark a burial site, simpler methods were available. Earthen mounds, stone circles, or basic cairns would have required far less effort. The choice to construct these umbrella stones implies a motivation beyond mere necessity. It suggests symbolism, identity, or perhaps a form of communication that has not survived in any decipherable form. Some researchers have proposed that the structures may have served as status markers, with larger or more elaborate stones indicating higher social standing. This hypothesis is supported by the presence of grave goods in certain excavated pits. However, the lack of consistent correlation between structure size and burial richness complicates this interpretation. Others have speculated about ritual or ceremonial functions, possibly related to ancestor worship. But without direct evidence, such theories remain speculative. There is also the question of spatial organization. While the stones appear scattered, closer analysis reveals subtle patterns in their distribution. Clusters form, distances repeat, and orientations show slight but measurable variation. Whether these patterns are intentional or coincidental is still debated. If intentional, they may encode information, social, ritual, or even cosmological, that we have yet to decode. What makes Kudakaluparambu particularly valuable is not that it provides answers, but that it exposes the limits of our current understanding. It challenges the assumption that technological sophistication must be visible, complex, or aligned with modern expectations. Here, the technology is hidden in plain sight, embedded in proportions, balance, and material choice rather than in overt mechanisms. It also highlights a recurring pattern in ancient engineering, the disappearance of knowledge. The people who built these structures left no written manuals, no inscriptions, no direct lineage of transmission. Whatever methods they used were either not recorded or not preserved. This is not unique. The composition of Roman concrete, the exact formulation of Greek fire, the drilling techniques evident in certain Egyptian stone cores, all represent cases where practical knowledge was lost despite its effectiveness. Kudakaluparambu may belong to this same category, a silent demonstration of competence without continuity. If these were just graves, why build them this precisely? What do you think they were really for? Share your thoughts below. In the Scottish Highlands, just east of Inverness, a circle of stones waits for the darkest sunset of the year. Clava Cairns was not discovered as a buried lost city. It survived in plain sight near the River Nairn, recorded by antiquarians in the 18th and 19th centuries, then studied more carefully by archaeologists who realised this was not just a Bronze Age cemetery, but a planned landscape of stone, light, geometry, and ritual memory. At first glance, the site looks simple. 3 circular cairns, standing stones, passages, and low stone chambers. But the closer you look, the stranger it becomes. Built around 4,000 years ago, probably between 2300 and 2000 BZ, Clava Cairns belongs to the early Bronze Age of northern Scotland. This was a world without written records, without steel tools, without the wheel being used for heavy construction in Britain, and without anything resembling a modern surveying instrument. Yet the builders created a monument that seems to lock architecture to the sky with a level of intention that still unsettles researchers today. The most extraordinary feature is the winter solstice alignment. The 2 outer cairns at Balnoran of Clava are passage graves, and their entrances face southwest, toward the place where the sun sets around midwinter. This is not a vague symbolic direction. At the darkest time of the year, when the sun travels at its lowest arc across the highland sky, the final light of sunset can shine directly along the narrow passage and into the central chamber. In other words, the structure appears to have been designed so that the dead, sealed inside stone would be touched by the returning sun at the exact turning point of the year. That single alignment creates the central engineering puzzle of Claver Cairns. To build it, the people had to know where the midwinter sun would set on the local horizon. They had to choose the position of the entrance, the angle of the passage, the height of the stones, and the shape of the chamber so the light would not be blocked. A difference of only a few degrees could have ruined the effect. A slightly wrong passage angle would send the beam into the wall. A slightly lower lintel or misplaced curbstone could cut off the light completely. This was not something a builder could correct easily after the cairn was finished, because each monument was made of heavy stones packed into a stable circular mass. Modern researchers often compare this with Newgrange in Ireland, where the winter solstice sunrise enters a roof box and lights the inner chamber, and with Maeshap in Orkney, where the midwinter sunset reaches deep into the tomb. But Claver Cairns is not just copying those monuments. Newgrange is larger and more dramatic, built around 3200 BC, more than 1,000 years earlier. Maeshowe is also older and architecturally more massive. Claver is smaller, but its precision is different. It uses a low highland horizon, southwest-facing passages, circular cairns, graded standing stones, and a cemetery layout that repeats the same solar logic more than once. The mystery is not whether the builders noticed the sun. The mystery is how they translated repeated sky observations into stone architecture with such confidence. To understand the difficulty, imagine standing in the same landscape 4,000 years ago. There is no compass. There is no map. There is no written calendar. The winter solstice itself is not a single visible object in the sky, but a slow annual pause when the sun's setting point reaches its furthest southern limit and then begins to move back. To identify that turning point, observers would need to watch the horizon day after day, probably year after year. They would need fixed markers, memory, tradition, and a shared system for passing knowledge across generations. The construction of Claver Cairns may preserve the result of long-term astronomical observation, but the tools behind that observation have vanished. The passage was also a light machine. Its purpose was not only to point toward the sun, but to control light inside darkness. The builders shaped a narrow approach so that sunset could behave like a beam inside a stone tunnel. This required an understanding of shadow, horizon height, seasonal movement, and the way low sunlight enters enclosed space. In modern terms, it resembles optical planning, but made with stone and experience instead of calculation. At Claver, architecture did not merely shelter the dead, it staged a rare solar event. The standing stones deepen the puzzle. Around the cairns, stone circles were arranged with clear differences in height. The tallest stones stand toward the southwest, close to the direction of the midwinter sunset, while smaller stones tend to appear toward the northeast. This height grading is too systematic to dismiss as accident. It suggests that the whole monument was designed as a visual and astronomical composition, not merely a burial mound surrounded by random boulders. The stones may have framed movement, guided sightlines, or emphasized the direction where the sun disappeared at the most important moment of the year. Even the colors of the stones seem to have been selected. Archaeological studies have noted that stones at Claver were not placed without pattern. Larger, redder stones are associated more strongly with the southwest, while smaller, lighter stones appear more toward the northeast. If this was deliberate, then the builders were not simply collecting whatever rocks were closest. They were choosing material by appearance, texture, and perhaps symbolic meaning. Red stone in the direction of the dying winter sun could have represented blood, fire, life, sunset, or rebirth. Lighter stones in the opposite direction may have created a contrast between darkness and return, death and renewal. No written explanation survives, but the pattern suggests a design language built into the monument itself. The geometry is just as important. Each cairn is circular, with a chamber at the centre, curbs around the mound, and a surrounding stone circle. To build this, people had to establish a central point, maintain a radius, and keep the passage aligned while the cairn grew outward. A simple rope could create a circle, but using that method across a complex structure still requires planning. The central chamber, the entrance passage, the curb, the outer ring, and the standing stones had to work together. If the cairn was built layer by layer, the builders needed a way to preserve the intended axis during construction. That means Clava cairns was not only ritual architecture, it was practical geometry in stone. The engineering becomes even more impressive when the weight of the material is considered. Some of the standing stones weigh several tons. They were not shaped into perfect blocks like Egyptian limestone or Roman masonry. They were irregular natural stones, difficult to grip, drag, lift, and set upright. In a Bronze Age community with limited metal tools, transporting and positioning these stones would have required coordinated labour, wooden sledges or rollers, ropes, levers, prepared ground, and a strong knowledge of balance. Unlike Stonehenge, where the largest sarcens weigh around 25 tons and the blue stones travelled from Wales, Clava cairns does not overwhelm by mass. Its challenge is subtler. Many stones had to be placed in a planned relationship to the horizon, the cairns, and the direction of sunset. The cairns themselves were built using dry stone construction without mortar. This matters because the site has survived for roughly 4 millennia in a wet northern climate, through frost, rain, soil movement, vegetation, collapse, reuse, and human disturbance. Dry stone building depends on pressure, weight distribution, and the careful locking of stones. A poorly built cairn would slump. A badly supported passage would collapse. A weak chamber would fail under the pressure of the mound. The survival of Clava cairns suggests that the builders understood structural stability at a level gained from long experience. There is also a strange contrast between burial and access. The two outer cairns have passages leading to central chambers, but the middle cairn is a ring cairn with no passage into a sealed burial chamber. It seems to have been designed differently, perhaps for ceremonies rather than repeated entry. This raises a difficult question. Was Clava cairns built mainly for the dead or for the living who gathered around the dead at certain times of the year? If the solstice sunset entered the passage only briefly, then the most powerful moment may have belonged not to daily use, but to a rare ceremony when light, stone, ancestors, and season converged. In the ruins of Aphrodisias in southwestern Turkey, there stands a structure that feels less like architecture and more like a controlled system. The Sebastion of Aphrodisias, built in the 1st century CE to honour the emperors of the Roman Empire, is not simply a ceremonial space. It is a corridor nearly 90 metres long, bordered by multi-storey walls that once carried more than 80 large marble reliefs. These reliefs were not randomly placed. They were arranged in a strict visual sequence, guiding the observer through mythology, conquest, and imperial authority. The central mystery is not the imagery itself, but the precision behind it. How material, structure, and narrative appear engineered with a level of consistency that challenges what we assume about ancient technical capability. The Sebastion did not reveal itself as a complete monument. Its modern story began in fragments during the 20th century, when archaeologists, most notably Keenan T., Erim began systematic excavations in the 1960s. What they encountered was not an intact structure, but a field of scattered components, collapsed walls, reused marble blocks, and relief panels embedded into later constructions. At first, these fragments seemed disconnected, but as excavation seasons progressed, patterns began to emerge. Relief panels were identified not as isolated artworks, but as parts of a larger composition. By the 1980s, enough material had been catalogued to reconstruct significant portions of the facade. Archaeologists determined that the corridor had been flanked by two parallel walls, each rising in multiple tiers, with sculptural panels arranged in vertical registers. Each register carried a different category of imagery gods, heroes, emperors, and personified regions of the empire. This was not decoration. It was sequencing. The site gradually revealed itself as a dismantled narrative architecture, one that had been designed to deliver information in a controlled visual order. In this sense, the discovery was not just physical, but conceptual. The realization that the Sebastian functioned as a structured system rather than a static monument. Aphrodisias was famous in antiquity for its marble quarries, producing a fine-grained calcite stone with crystal sizes, often below 1 millimeter and relatively low impurity levels. Such material allows for high-detail carving, but the Sebastian pushes this advantage into a range that raises deeper technical questions. Detailed measurements of surviving reliefs show extremely controlled carving depths. In many panels, transitions between foreground figures and background surfaces occur within just a few millimeters, creating smooth gradients of shadow that resemble modern bas-relief techniques. Anatomical features, muscle tension, facial symmetry, even the layering of fabric are executed with remarkable consistency across multiple panels. Scientific analysis of symmetry indicates deviations, often within 1 to 2 millimeters across bilateral features of faces. For hand-carved stone, repeated at scale, this level of accuracy is difficult to explain without some form of guiding system. Roman sculptors are known to have used iron chisels, claw chisels, and abrasives such as emery, but these tools alone do not fully account for the uniformity observed. Microscopic studies of tool marks reveal another anomaly. Surface finishing appears to follow consistent, multi-stage processes. Certain areas are deliberately left matte, while others are polished to higher reflectivity. This suggests that artisans were not only carving forms but also engineering how light would interact with different textures. The result is a controlled visual effect, one that changes depending on viewing angle and illumination. When compared with other Roman achievements such as the structural precision of the Pantheon or the realism of imperial portrait sculpture, the Sebastian stands out for the density of fine detail per surface area. It is not simply well made, it is consistently precise. Several hypotheses attempt to explain this. One suggests the use of early pointing devices, mechanical systems, for transferring proportions from a model to stone. While these are documented in later periods, direct evidence for their use at this scale in the 1st century is scarce. Another theory proposes a highly organized workshop system, where different artisans specialized in stages such as rough cutting, detailing, and finishing, all guided by strict proportional templates. Yet even these explanations leave gaps. The consistency across dozens of panels, potentially produced over long periods, suggests not only skill but process control. The marble was not just carved, it was processed in a way that approaches repeatability, a concept closer to engineering than traditional craftsmanship. Beyond the material itself, the Sebastian reveals a second layer of precision: standardization in imagery. Figures across different panels share consistent proportions, similar poses, and recurring anatomical structures. Heads align with comparable ratios to body height. Limbs follow repeated geometric relationships, and stances are variations of a limited set of base forms. This suggests the use of templates or canonical models. Inscriptions and stylistic differences indicate that multiple sculptors work simultaneously, yet the final output remains cohesive. This implies centralized planning, a design system that ensured consistency across independent contributions. Such standardization was not unknown in the Roman Empire. It can be seen in coin production, military equipment, and architectural modules. However, applying it to narrative relief sculpture at this scale is unusual. Here, standardization is used not to simplify production, but to maintain a unified visual language across a complex ideological program. The result is a form of controlled variation. Each panel is unique, yet all belong to a single system. This balance between repetition and difference is a hallmark of structured design. The Sebastion is not only about what is carved, but how it is experienced. The corridor's proportions, long, narrow, and enclosed, create a directional flow that guides movement forward. Visitors would not wander randomly. They would be led through a controlled path. The vertical arrangement of reliefs adds another layer. Lower panels are easily visible, while upper tiers require the viewer to look upward, shifting attention across multiple levels. This creates a structured viewing sequence, forcing engagement with the imagery in a specific order. Lighting plays a critical role. Studies suggest that sunlight would have entered the corridor at particular angles throughout the day, selectively illuminating certain panels while leaving others in shadow. This dynamic interaction between light and relief enhances depth perception and emphasizes different parts of the narrative over time. Such coordination implies intentional design. While Roman architects understood orientation and illumination, the level of integration here suggests something more deliberate, an early form of perceptual engineering. The space does not simply contain images, it controls how those images are perceived. Do you think the Sebastion is simply the peak of ancient craftsmanship, or evidence of a technical system we still don't fully understand? Share your thoughts in the comments below. Hundreds of stone chambers stand exposed under the open sky, scattered across a rocky hill in southern India. No inscriptions explain them, no surviving city surrounds them, and yet each structure follows a logic, repeated, deliberate, and disturbingly consistent. The site is known today as the Higher Bengal Dolmens, a megalithic complex dated to roughly 1200 to 500 BCE. At first glance, they appear primitive, but the closer they are studied, the harder they are to explain. The site entered academic awareness in the 19th century during the expansion of archaeological surveys under British colonial administration in India. Early observers noted the unusual density of dolmens, stone-built burial chambers, spread across the granite hills of what is now Karnataka. Unlike isolated megaliths found elsewhere, here Bengal presented something different, a concentrated field of structures extending over several hectares. Systematic documentation began in the early 20th century, but it was not until later archaeological work that the scale became clearer. Surveys identified more than 400 dolmens in the immediate area, with estimates rising significantly when including surrounding clusters. Radiocarbon dating and typological comparisons linked the site to the South Indian Iron Age, placing it within a broader megalithic tradition that stretched across the Deccan Plateau. Yet from the beginning, a contradiction was apparent. Sites of this scale typically correlate with large organized settlements. Here, the expected urban counterpart was missing. Subsequent excavations revealed that many of the dolmens functioned as burial chambers, Inside, archaeologists discovered human skeletal remains, pottery fragments, iron tools, and occasionally beads made from semi-precious stones. These findings confirmed that the site was part of a funerary tradition, likely tied to ritual practices surrounding death and ancestry. However, the material record introduced new questions rather than resolving old ones. The iron objects suggested a community with metallurgical knowledge, yet no large-scale production sites were found nearby. The pottery styles showed consistency, implying cultural continuity, but offered little insight into the organization required to construct hundreds of stone structures. More striking was the spatial arrangement. The dolmens were not randomly placed. Many were positioned along ridges or elevated terrain, suggesting intentional placement rather than convenience. Some appeared grouped, forming loose clusters that hinted at social or familial divisions. But without written records, these patterns remain speculative. The most immediate puzzle lies in the imbalance between the scale of the burial complex and the absence of a corresponding settlement. If hundreds of individuals were buried here over generations, where did they live? In other parts of the world, large burial complexes, such as those associated with Bronze Age Europe, are typically linked to nearby habitation sites. At Stonehenge, for example, archaeological evidence points to surrounding settlements and seasonal occupation zones. Even when the living spaces were temporary, traces remained: post holes, hearths, refuse deposits. At Higher Bengal, such evidence is limited or ambiguous. One explanation is preservation bias. Structures built from wood or organic materials may have decayed beyond recognition. Another possibility is that the site functioned as a regional ritual center, drawing communities from a wider area rather than serving a single settlement. If so, the dolmens may represent not a village cemetery, but a shared sacred landscape. Yet this interpretation raises further questions. Organizing repeated construction at this scale would require coordination across groups, shared beliefs, and long-term continuity. In the absence of centralized authority or written systems, how was such coordination achieved? Each dolmen follows a deceptively simple design: vertical stone slabs forming a chamber, capped by a large horizontal stone. There is no mortar, no intricate carving, no visible mechanical complexity. But this simplicity is misleading. The stones used in these structures are not small. Individual slabs can weigh several tons. Transporting them across uneven terrain would have required coordinated labor, even with basic tools. Placing the armed capstone, often balanced with surprising stability, would have demanded precise control over weight distribution and alignment. Experimental archaeology has attempted to replicate similar constructions using only technologies available to Iron Age societies: wooden rollers, earthen ramps, and manual labor. While such methods are theoretically sufficient, they require careful planning and a large workforce. Even minor errors in positioning could result in collapse or instability. What makes Higher Bengal particularly intriguing is the consistency of execution. Across hundreds of structures, the same basic architectural logic is repeated with minimal variation. This suggests not improvisation, but a shared construction knowledge, possibly transmitted across generations. In some cases, dolmens are positioned on sloped or uneven ground. Achieving stability in such conditions implies an understanding of balance and load distribution that goes beyond trial and error. There are no written manuals, no diagrams, no surviving tools that fully explain how this knowledge was formalized. Compared to monumental sites like Stonehenge, which display complex astronomical alignments and shaped stones, the dolmens of Higher Bengal appear technically modest. Yet the challenge here is different. Instead of a few highly engineered structures, we see hundreds of repeatable units, each requiring reliable, scalable methods. In modern engineering terms, this resembles a system optimized for replication rather than uniqueness. The unresolved question is not whether these structures could be built, but how such consistency was maintained without documented standards. One of the most distinctive features of many higher Benkel dolmens is the presence of circular openings carved into one of the vertical slabs. These portholes are often too small to allow human entry, yet too deliberate to be accidental. From a purely functional perspective, such openings are unnecessary for burial. Bodies could be placed before sealing the chamber. The effort required to carve a circular hole into a large stone slab using tools of limited hardness suggests that the feature held significance. Several hypotheses have been proposed. The openings may have served as symbolic gateways, allowing interaction between the living and the dead. They may have been used for ritual offerings, enabling the placement of food or objects inside sealed chambers. Another possibility is that they functioned as ventilation or drainage points, though their placement does not always support this interpretation. What complicates the picture is their standardization. Many portholes share similar acar and positioning, implying a shared template or cultural rule. Achieving such regularity without advanced drilling tools raises questions about the techniques employed. Repetitive pecking, abrasion with harder stones, and controlled fracturing are all possible methods, but each would require time, skill, and consistency. In archaeological terms, the portholes represent an investment of labor beyond immediate necessity. They're a deliberate addition to the structure, one that encodes meaning we do not yet understand. Beyond individual structures, the broader layout of the site suggests intentional organization. Many dolmens are aligned along natural contours of the landscape, particularly ridgelines. Elevated placement may have had symbolic significance, associating the dead with visibility, prominence, or proximity to the sky. Attempts have been made to identify astronomical alignments, as seen in sites like Stonehenge or Machu Picchu, where solar and lunar cycles are embedded into architecture. At Higher Benkel, evidence for such alignments remains inconclusive. Some orientations appear non-random, but no consistent pattern has been universally accepted. What is clear is that the builders were making choices. The placement of each dolmen was not purely opportunistic. It reflected a set of criteria, geographical, cultural, or symbolic, that guided construction over time. If a society left behind a system this organized, this consistent, and this technically demanding, why did they leave behind no trace of how it was done? What do you think really happened here? Share your theory in the comments below. At an altitude of over 5,000 meters in the remote reaches of the Himalayas, a small glacial lake appears unremarkable for most of the year. Frozen, isolated, and inaccessible, it blends into a landscape shaped by ice and silence. But when the snow melts, the surface reveals something that should not exist in such numbers or in such a place. Hundreds of human skeletons scattered along the edges of the water, preserved by cold and time. The problem is not simply that these people died here. The problem is that they did not die together, did not come from the same place, and yet appear to have met the same end. Rupkund Lake is not a single mystery. It is a pattern of events repeating across centuries without a clear explanation. The modern story begins in 1942, when a British forest ranger, patrolling the region during the late colonial period of India, came across a disturbing sight. As the ice receded, human bones began to emerge across the lake bed and surrounding slopes. Initial assumptions were shaped by the context of the time. With the Second World War underway, officials speculated that these might be the remains of Japanese soldiers who had attempted an incursion through the mountains. However, closer inspection quickly dismantled this theory. the skeletal remains showed clear signs of age far beyond a few decades. No modern weapons, uniforms, or equipment were found. Instead, artifacts such as wooden tools, leather footwear, iron spearheads, and rings suggested a much older origin. What began as a wartime curiosity immediately transformed into an archaeological anomaly. By the 1950s and 60s, systematic examinations of the bones began. Anthropologists noted that many of the skeletons were remarkably well preserved due to the freezing conditions, allowing for detailed study. One of the most striking findings was the pattern of injuries. A large proportion of skulls displayed circular fractures, consistent with blunt force trauma delivered from above. These were not random breaks caused by erosion or animal activity. The injuries were concentrated on the top of the skull, with minimal damage to other parts of the body. This distribution ruled out close combat or interpersonal violence. Instead, it suggested a sudden, external force acting vertically. Based on these observations, researchers proposed a hypothesis grounded in environmental physics. At high altitudes, hailstorms can produce ice projectiles with diameters exceeding 5 centimeters and impact velocities sufficient to fracture bone. If a group of individuals were caught in an exposed area without shelter, repeated impacts could cause fatal head injuries within minutes. This explanation aligned with both the injury patterns and the lack of defensive wounds. However, it did not explain who these people were, why they were there, or why so many died in the same location. In the early 2000s, advances in radiocarbon dating provided the first reliable timeline. Initial tests suggested that a significant portion of the remains dated to approximately the 9th century. This placed the event more than 1,000 years before the modern discovery. The implication was clear. These individuals were not linked to any recent historical conflict, but to a much older, undocumented event. The number of individuals estimated between 200 and 800 indicated that this was not a small group. It was a large, organized movement of people. Further analysis of clothing fragments and artifacts revealed diversity within the group. Some individuals wore simple, practical garments consistent with local populations. Others were associated with more elaborate items, including ornaments and decorated objects. This suggested a mixed group, possibly including both common travelers and individuals of higher social status. One hypothesis proposed that they were part of a pilgrimage, possibly connected to ancient Himalayan religious practices. Yet, no written records from the period clearly describe such a large group meeting this fate in this location. In 2019, a comprehensive genetic study introduced a new layer of complexity. Using ancient DNA sequencing, researchers analyzed dozens of individuals from the site. The results fundamentally altered the understanding of Rupkund. Instead of a single group, the remains belonged to at least 2 distinct populations separated not only by geography, but also by time. One group was consistent with South Asian ancestry and dated to around the 8th to 10th centuries. This aligned with earlier radiocarbon findings and supported the pilgrimage hypothesis. However, a second group displayed genetic markers most closely associated with populations from the Eastern Mediterranean, including regions such as Greece and Crete. Even more surprising was the dating of this group. They appeared to have died roughly 1,000 years after the first group. This created a contradiction that current historical models struggle to resolve. There is no clear evidence of large-scale Mediterranean travel into this specific region of the Himalayas during that period. Nor is there an explanation for why these individuals would have followed a path leading to such an isolated and hazardous location. The presence of 2 unrelated groups, separated by centuries, yet ending up in the same lake, suggests that Rupkund is not the result of a single historical event. When all evidence is considered together, a pattern begins to emerge. Multiple groups from different regions and different centuries arrived at the same high-altitude lake. Each group appears to have died suddenly, with similar trauma concentrated on the skull. There is no evidence of long-term habitation, no signs of burial practices, and no indication that survivors remained to document the event. The deaths were abrupt and final. From a scientific perspective, the most consistent explanation remains extreme weather, specifically high-energy hailstorms. At elevations above 5,000 meters, atmospheric conditions can produce localized events of extraordinary intensity. Without modern forecasting or protective equipment, ancient travelers would have had no warning and no means of escape. Yet, this explanation raises its own questions. Why did multiple groups choose this route? Why were they exposed at precisely the same vulnerable location? And why does the pattern repeat across such long intervals? Rupkund Lake challenges the assumption that archaeological sites represent isolated events. Instead, it suggests the possibility of recurring environmental hazards interacting with human movement in ways that are not fully documented. The combination of radiocarbon dating, forensic analysis, and genetic data creates a layered narrative that does not resolve into a single conclusion. Each new discovery has added clarity to individual aspects: how they died, when they died, and where they came from, but has also expanded the scope of the mystery. If a single natural mechanism can produce identical outcomes across centuries, then Rupkund may represent a broader class of sites where environmental risk is underestimated or misunderstood. Alternatively, if there are missing historical connections, trade routes, undocumented migrations, or lost cultural practices, then the lake may be a fragment of a much larger story that has not yet been reconstructed. If multiple groups, separated by centuries and coming from entirely different regions, all ended up dying in the exact same way at the same location, do you think Rupkund is just a natural hazard repeated over time? Or are we missing a deeper pattern behind these events? Share your thoughts in the comments below. Toninar was not discovered in the dramatic, sudden way many ancient sites were. Instead, it emerged gradually from obscurity in the late 19th century, when explorers moving through the remote Ocosingo Valley in the highlands of Chiapas, southern Mexico, began documenting unusually massive stone terraces rising from the jungle floor. Early reports by researchers such as Desiree Charnay in the 1880s described a structure that did not resemble a conventional Maya city. What stood before them was not a spread of temples and plazas, but a single immense vertical formation. Later excavations throughout the 20th century, particularly those led by Mexico's National Institute of Anthropology and History, revealed the full scale of the site. A towering acropolis rising over 70 meters in height, composed of at least 7 superimposed terraces, making it one of the tallest structures in the entire Maya world. From the moment its layout became clear, Toninar presented a problem that has never been fully resolved. Unlike major centers such as Tikal or Palenque, which expand horizontally across wide ceremonial plazas, Toninar compresses its entire ceremonial and political core into a vertically stacked system. This is not a minor variation. It represents a complete departure from the spatial logic of Maya urbanism. The most immediate mystery is therefore structural. Why would a civilization known for expansive layouts choose instead to construct what is effectively a vertical city? The engineering implications alone are significant. Building upward at this scale in a tropical environment introduces challenges that horizontal cities largely avoid. Each terrace must support the cumulative weight of all structures above it, requiring precise load distribution across stone retaining walls. Archaeological analysis shows that these walls are not crude accumulations of rubble, but carefully constructed systems of fitted limestone blocks, some weighing hundreds of kilograms. The stability of the Acropolis over more than a millennium suggests a sophisticated understanding of pressure management and foundational support. Compared to other Maya constructions, where even modest pyramids required periodic reinforcement, Tonenar's survival in a region with seasonal rainfall exceeding 2,000 millimeters per year is difficult to explain without assuming deliberate over-engineering. Even more striking is the issue of water control. In steep, terraced environments, uncontrolled runoff typically leads to rapid erosion and structural collapse. Yet Tonenar incorporates subtle but effective drainage solutions, channels carved into stone, angled surfaces that direct water away from critical joints, and layered platforms that reduce hydraulic pressure. When compared with sites like Copan, where erosion has significantly damaged architectural features despite less extreme verticality, Tonenar appears disproportionately resilient. This raises a key question. Were its builders solving problems that did not yet exist, anticipating long-term environmental stress in a way that exceeds known Maya practices? The mystery deepens when examining how space is used within this vertical system. Movement through Tonenar is not free or open. It is guided, constrained, and often deliberately disorienting. Staircases are steep and narrow, forcing single-direction flow. Terraces limit visibility, preventing large-scale observation of ceremonies from a single vantage point. This contrasts sharply with the open plazas of sites like Chichén Itzá, where architecture is designed to accommodate large audiences and communal viewing. At Tonenar, spatial design appears to control not just movement but perception itself. This controlled environment becomes particularly significant when considering the site's massive ball court, one of the largest in Mesoamerica. Measuring over 100 meters in length, the court is embedded within the architectural framework rather than placed in an open civic space. Its elongated, enclosed design restricts both participation and observation, suggesting that the ballgame here may have functioned differently than at other Maya centers. While traditionally interpreted as a ritual tied to cosmology and myth, at Tonenar, it may have served as a form of controlled political performance, an event where outcomes and interpretations were tightly managed by elite authority. Archaeological evidence supports this interpretation. Tonenar is renowned for its unusually explicit sculptural program, which emphasizes domination, captivity, and violence. Numerous monuments depict bound prisoners, decapitated figures, and victorious rulers standing over defeated enemies. These are not abstract representations of power. They are direct, almost confrontational statements. Inscriptions found at the site document repeated military conflicts, particularly with nearby Palenque, one of Tonenar's primary rivals during the Classic period. Epigraphic studies indicate that Tonenar may have captured and even executed high-ranking individuals from competing cities, reinforcing its political dominance through both action and imagery. What makes this significant is not merely the presence of violence, but its integration into the architecture itself. At Tonenar, power is not confined to monuments or inscriptions, it is embedded into the physical experience of the site. As one ascends the terraces, the combination of steep elevation, restricted movement, and constant visual reminders of conquest creates an environment that may have been designed to influence psychological response. In this sense, the Acropolis functions less like a ceremonial center and more like a controlled spatial narrative, guiding individuals through a sequence of experiences that reinforce authority. Yet even this interpretation leaves critical questions unanswered. If Tonenar was primarily a political instrument, why invest such extraordinary effort into vertical construction rather than more conventional displays of power? If it was defensive in nature, why does it lack many of the features typically associated with fortifications, such as perimeter walls or strategic lookout points? And if it was purely ceremonial, why does its engineering exceed the practical requirements of ritual use? Some researchers have proposed that Toninar represents a localized architectural experiment, a deviation driven by regional conditions or specific cultural priorities. Others suggest that its design reflects a symbolic attempt to replicate sacred mountains, aligning the city with cosmological beliefs about the layered structure of the universe. However, these explanations remain partial. Neither fully accounts for the combination of advanced engineering, spatial control, and aggressive iconography that defines the site. In comparative terms, Toninar occupies an unusual position within the Maya world. It is neither the largest nor the most artistically refined site, yet it demonstrates a level of structural ambition that rivals or exceeds more famous centers. Its verticality has few parallels, and its integration of architecture, engineering, and political messaging appears unusually cohesive. This combination suggests that Toninar was not simply following established traditions, but actively redefining them. Ultimately, the greatest mystery of Toninar may not lie in any single feature, but in the convergence of all its anomalies. It is a site where architectural form, environmental adaptation, and ideological expression intersect in ways that challenge existing models of Maya civilization. Despite decades of excavation and analysis, no single framework has been able to fully explain its design. Toninar stands, therefore, as more than an archaeological site. It is a question in stone, one that forces us to reconsider what ancient cities were meant to be, and whether some of them were built not just to function, but to shape how people think, move, and perceive power itself. Jarkoton did not emerge from the ground as a dramatic, singular discovery. It began with fragments, scattered pottery, faint outlines of walls, and subtle anomalies in the soil recorded during Soviet-era surveys in southern Uzbekistan in the 1970s. At first, it seemed like just another minor Bronze Age settlement, but as excavation expanded, the scale shifted dramatically. What lay beneath was not a village, but a structured urban center covering dozens of hectares, dated roughly between 1500 and 1300 BCE, associated with the Sapali culture. And from that moment, the site began to contradict expectations. Conventional models of Bronze Age development suggest that complex urban systems emerged in a limited number of core regions, primarily Mesopotamia, the Indus Valley Civilization, and the Nile Valley. Central Asia, by contrast, has often been framed as a transitional zone dominated by pastoral or semi-nomadic groups. Jarkoton challenges that assumption. Excavations reveal defensive walls, organized residential sectors, and a central complex that appears to serve ritual or administrative functions. The layout suggests planning rather than organic growth. To put this into perspective, cities like Mohenjo-Daro in the Indus Valley, dated to around 2600 BCE, exhibit grid-based planning and drainage systems. Jarkoton, though later by nearly 1,000 years, appears in a region where such planning was not expected at all. This raises a critical question. Was urbanization in Central Asia independently developed, or was it influenced by distant civilizations through networks we still cannot fully trace? Perhaps the most unsettling contradiction at Jarkoton lies not in what was built, but in how it has survived. The city was constructed primarily from mud brick, an unbaked mixture of clay, water, and organic material. By all conventional engineering standards, mud brick is among the least durable building materials. In environments with temperature fluctuation, wind erosion, and seasonal moisture, such structures degrade rapidly. often within decades or centuries at most without continuous maintenance. And yet, at Jarchoton, large portions of walls, foundations, and architectural outlines remain identifiable after more than 3,000 years. This is not entirely unique, but the degree of preservation is unusual. For comparison, mud brick architecture in Mesopotamia often survives only as low mounds, heavily eroded and difficult to reconstruct without extensive interpretation. Even in relatively stable desert environments like parts of Egypt, mud brick structures typically require protective conditions, burial under sand, minimal rainfall, or deliberate conservation to remain intact over millennia. Jarchoton presents a more complex case. The site has been exposed, subject to environmental stress, yet still retains structural clarity. This leads to several unresolved possibilities. One hypothesis suggests advanced preparation techniques, specific ratios of clay to organic binders, controlled drying methods, or even unknown additives that increase durability. However, chemical analyses so far have not identified any dramatically unusual composition. Another possibility is environmental, that ancient climatic conditions in the region were significantly different, perhaps drier or more stable, reducing long-term erosion. Paleoclimate studies do indicate shifts in Central Asian climate over the past several thousand years, but not at a scale that fully explains the preservation seen here. A third, more subtle explanation is architectural intelligence design choices that minimized exposure, such as wall thickness, orientation relative to prevailing winds, or structural layering that slowed degradation. In other words, the material itself may be simple, but the way it was used could reflect a level of environmental adaptation that we are only beginning to understand. Still, none of these explanations fully resolves the contradiction. Mud brick should not last this long, under these conditions, with this level of clarity. And yet, at Jarchoton, it does. Among the most debated features of Jarchoton is its ritual complex, where archaeologists have identified structures interpreted as fire altars. These installations bear a conceptual resemblance to later practices associated with Zoroastrianism, in which fire plays a central symbolic role. The problem is chronological. Zoroastrianism, as a formalized religious system, is generally dated to the early 1st millennium BCE, although its origins may extend earlier. Jarchoton predates this by several centuries. If the interpretation is correct, it suggests that elements of fire-centered ritual practice existed long before they were codified into a structured religion. Alternatively, the resemblance may be superficial, similar forms arising independently in different cultural contexts. Without written records, the function of these structures remains speculative, but their presence indicates that Jarchoton was not merely a settlement. It was a place where symbolic or ritual behavior was spatially organized and architecturally embedded. Artifacts recovered from Jarchoton complicate its isolation. Pottery styles, beads, and certain material forms show parallels with regions far beyond Central Asia, including the Indus Valley civilization and areas connected to Mesopotamia. This suggests participation in broader exchange networks, possibly linked to what archaeologists describe as the Bactria-Margiana archaeological complex, a system of interconnected settlements spanning parts of modern Turkmenistan, Uzbekistan, and northern Afghanistan. However, unlike Mesopotamia or the Indus Valley, where written records and well-defined trade routes provide context, Jarchoton exists in relative silence. There are no inscriptions, no administrative tablets, no direct evidence of organized long-distance trade infrastructure. The implication is paradoxical. Material evidence points to connectivity, but the mechanisms of that connectivity remain invisible. Equally puzzling is how Jarchoton ended. Archaeological layers do not show signs of violent destruction, no widespread burning, no mass casualties, no abrupt collapse. Instead, the evidence suggests gradual abandonment. This pattern aligns with broader regional transitions during the Late Bronze Age, when climatic shifts, changes in water availability, or evolving trade dynamics may have altered settlement viability. Yet in Jarkoton, the data is incomplete. There is no single event, no clear tipping point, only a slow fading from occupation into silence. Jarkoton is not the largest or most advanced city, but it does not align with any established historical model. It introduces urban planning in a region where it was not expected, preserves mud brick architecture beyond normal limits, suggests ritual systems earlier than recorded history, and shows signs of trade without leaving clear traces. Then it disappears without a specific cause. Jarkoton does not break history, it exposes its gaps. What do you think Jarkoton really represents, an isolated anomaly, or evidence of a forgotten system of early civilization? Share your thoughts in the comments below.